I think we're live.
Okay, it's working.
Mm-hmm.
Yeah, let's give it one or two more minutes and then we can get started. Okay, I think we can get started. We have quite a few people here and online. Okay, welcome everyone to the first Safari live seminar of the fall 2022 semester. This time we have a Safari veteran, Hassan, who's going to give the seminar. Hassan has been a PhD student with me for about 6 years now, and he's been doing exciting research on DRAM in general, various aspects of DRAM. And he's going to give a detailed overview of his dissertation, improving DRAM performance, reliability, and security by rigorously understanding intrinsic DRAM operation, which he's going to defend 2 weeks from now. Hasan got his bachelor's degree at TOB University in Turkey, and then master's also there, and he joined Safari at CMU as an intern, and after that he continued as a PhD student, and he's coming to the end of the PhD journey very soon. With that, I think we can get started. Feel free to ask questions here on Zoom as well as on YouTube. We'll be monitoring questions, and hopefully let's have a nice scholarly discussion. Hasan, please go ahead.
Yeah, thanks for the introduction, Anu. And yeah, so please feel free to interrupt me and ask questions right away. Okay, so today I will talk about the work I've done during my PhD, and I will start with a brief introduction to DRAM and its history. So DRAM stands for Dynamic Random Access Memory, and it has been prevalently used as the main memory in various computing systems since 1970s. In 1968, Dennard was granted the patent for one transistor DRAM cell. So like this was like, I guess, the first time DRAM was introduced in the history. And then in 1917, the first commercial available DRAM integrated circuit appeared, which had only 1 kilobit capacity. Later in 1992, Samsung developed the first synchronous DRAM, which had 16 megabit capacity. So like this DRAM type is sort of similar to DRAM chips we have today. And 5 years later, the DRAM capacity increased to 64 megabits, and the first DRAM chip was standard. And this was the first DRAM chip with the standardized DDR interface. Fast forwarding to 2022, today we have DRAM chips with densities up to, and actually maybe even more than 32 gigabit. And over the last 2 decades, DRAM chip density improved greatly due to continuous manufacturing technology node scaling. And today, these DRAM chips power various computing systems, including GPUs, personal computers, servers, safety-critical systems, and mobile devices. Obviously, it is desirable to increase the DRAM chip density even further for increasing the main memory capacity. However, transitioning to smaller technology nodes exacerbates the scaling challenges of DRAM. And what are the scaling challenges of DRAM? So as DRAM cells become smaller and distances between cells reduce, ensuring data integrity becomes an increasingly critical problem. Often ensuring reliable DRAM operation limits the minimum latency for accessing DRAM. So typically, DRAM vendors make design decisions that affect data integrity versus latency trade-off in DRAM. Consequently, DRAM scaling challenges affect the system performance, energy efficiency, reliability, and security. To combat the system-level implications of the DRAM scaling challenges, our goal is to first build an infrastructure for characterization, analysis, and understanding of real DRAM chips. And second, enable new mechanisms for improving all these four aspects: performance, energy efficiency, reliability, and security. We make four core contributions to address the scaling challenges of DRAM. Our first contribution is Softmc, which is a flexible and easy-to-use FPGA-based DRAM characterization infrastructure. Second, we develop U-TRR, which is a new methodology to uncover the inner workings of in-DRAM RowHammer protection mechanisms and studying their security properties. Our third contribution, self-managing DRAM, is a simple interface and DRAM architecture for enabling autonomous in-DRAM maintenance operations. And finally, Crow is a low-cost substrate for improving DRAM performance, energy efficiency, and reliability. Now we will go into each of these four works, and we will start with Softmc. But before that, I would like to go over some DRAM background very quickly. Here, I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside the DRAM chip, there are multiple banks, which contain many DRAM cells organized as two-dimensional array. The DRAM cell stores a single bit of information as electrical charge. In a bank, the cells are vertically connected to sense amplifiers, which can read the data from the cells and update it when needed. And the cells are organized horizontally as DRAM rows. Now let's look at DRAM commands that the memory controller issues to access the DRAM. To perform an access, the memory controller first activates or opens a row from a bank by issuing an activate command. The activate command loads rows data into the sense amplifiers where the data can be accessed. After the row is accessed, the memory controller issues a precharge command to close an open row so that a new row from the same bank can be activated. Okay, so basically these are like the four main commands that are involved in the DRAM access: activate, read-write commands, and the precharge command. Each DRAM cell encodes data in fundamental leaky capacitors. Here's a simplified diagram of a DRAM cell where the capacitor in blue, the capacitor in yellow stores the data and the access transistor gates access the data. There are a number of leakage paths which the charge can enter or exit the capacitor. The important thing to note is that the stored data can be corrupted if too much charge leaks from the cell or from the cell capacitor. Here's a simplified diagram of the capacitor voltage over time. We see that the voltage degrades over time in an exponential decay. There is a threshold Vmin under which we can no longer guarantee that the data will be read correctly. As long as the cell's voltage remains above this line, we consider this a retention success. However, as soon as the voltage drops below Vmin, we consider this as retention failure. In order to prevent failures from charge leakage known as retention failures, periodic refresh operations are issued to recharge the cell capacitor voltage. So the memory controller performs this operation by issuing refresh commands. The interval between refresh commands are referred to as the refresh window. Okay, now moving on to the contributions, and I will first introduce our Softmc infrastructure. Many factors that affect DRAM reliability and latency cannot be properly modeled in simulation or analytically. One such factor is DRAM access timings. Here we illustrate how charge levels of a DRAM cell and sense amplifier change when using the activate, read, and precharge commands. The memory controller normally issues these commands by respecting the corresponding timing parameters, here denoted as ready-to-access latency, activation latency, and precharge latency. So what will happen if the memory controller somehow violates the ready-to-access latency and issues the read command earlier than it is supposed to? So issuing the read command sooner will not provide enough time for the sense amplifier to raise its charge to a level that data can be reliably accessed. And this may result in reading incorrect data. Similarly, issuing the precharge and the next activate command sooner than the designated timing parameters may result in bit flips. Besides violating DRAM timing parameters, other factors that affect DRAM reliability and latency are intercell interference, manufacturing process variation, temperature, DRAM supply voltage, and many other factors. Because many of these factors cannot be properly modeled in simulation or analytically, we need to characterize, analyze, and understand the behavior of real DRAM chips to design, evaluate, and validate mechanisms that could improve DRAM reliability and performance. Next,
Hassan, I have a quick question on this. So I think your goal is to build an understanding of the reliability and latency. And this DRAM timing violation, I think I can guess why you're doing it, but maybe it's good to explicitly say that. Why would you ever want to look at the effects of DRAM timing violations?
Well, so one reason is, although here we show an example of one cell, not all DRAM cells or all DRAM chips are equal, meaning some DRAM cells can tolerate or can be reliably accessed with lower timing parameters, lower than like what the DRAM datasheet says, for example. And this is basically an opportunity for improving performance and energy efficiency. So understanding all these aspects is important to be able to develop mechanisms that will exploit that variation.
Okay, makes sense. So you by understanding the variation in the latencies, reliable access latencies, by violating the timing parameters, you can perhaps come up with a new mechanism that can exploit that variation.
True.
Okay.
Okay, next, I would like to explain the two goals that we believe a DRAM characterization infrastructure should achieve. First, a memory testing infrastructure should be flexible so that it can support any DRAM operation. This includes an ability to test any DRAM operation and the ability to test any combination of DRAM operations with custom timing parameters. Second, the infrastructure should be easy to use. It should have simple and intuitive programming interface that minimizes programming effort and time. It should be accessible to a wide range of users, even users that lack experience of hardware design should be able to perform DRAM tests. So we designed our infrastructure to achieve these two goals. Softmc is the first publicly available FPGA-based DRAM characterization infrastructure. It is easily programmable using its C++ API. This photo shows an example Softmc setup where the FPGA runs Softmc and has a DRAM module attached to it. The Softmc user controls the experiments with programs that run on the host machine connected to the FPGA via the PCIe interface. To perform temperature-controlled experiments, this setup sticks two heater pads around the DRAM modules and adjusts the temperature of the DRAM chips using a temperature control shown on the right. To control DRAM supply voltage, this setup also includes an external power supply unit that powers the DRAM module. Softmc has three key components: the Softmc API, the PCIe driver, and the Softmc hardware. So let's first talk about the Softmc API. In the API, we provide a set of C++ functions and structures that minimize programmers' effort. In this presentation, I won't go over the API in detail. Instead, I will demonstrate how the API is used by a simple code example. For more details, please refer to our paper or the source code. The API provides a set of instruction generator functions. Programmers use these functions to generate instructions that tell the hardware to perform specific operations. For example, these functions such as generate activate is basically a function that generates an instruction for the FPGA that, on the other hand, forwards an activate command to the DRAM module. And here the second function is just basically to control the timings between multiple DRAM commands that will be executed in sequence. So this generate wait puts some idle cycles between the two commands. In this example, between activate and the next instruction, which will be the write. Yeah, so similarly, we have like separate instructions for generating a write command, for pre-charge command, and here at the end, we have just a function to indicate that this is the end of the Softmc program. Okay, so the structure that we have here, which stores or contains the program information, is called instruction sequence. And once this instruction sequence is populated with all the commands that the Softmc hardware will execute, these are sent at once to the FPGA over the PCI interface, and these instructions start executing immediately. Okay, so I won't talk about much about the PCIe driver. This is just like, we use the stock PCIe driver provided by Xilinx, which is the manufacturer of the FPGA boards that we use. But I would like to talk about, in a bit more detail about the Softmc hardware. This slide depicts the host machine, the DRAM module, and the FPGA that implements the Softmc hardware. I would like to show how the hardware operates by an example. On the host machine, using the Softmc API that I presented in the previous slide, the programmer generates a set of Softmc instructions. Then the driver sends these instructions over the PCIe bus to the Softmc hardware. In the Softmc hardware, the instructions are buffered in the instruction queue. After receiving the entire instruction sequence, the instruction dispatcher fetches instructions from the queue and executes them. Let's assume the first instruction is an activate, using which we can open a row from the DRAM module. For that instruction, the dispatcher creates a corresponding DRAM command, which the DDR5 unit sends to the DRAM module via the DDR bus. Next, the dispatcher fetches the next instruction from the instruction queue. And this instruction here happens to be a wait, which basically designates the ready to access latency between the activate command and the next command to follow. And here the instruction dispatcher does not generate a DRAM command, obviously, because this operation, just waiting, does not involve in the operation from the DRAM side. Okay, and the third and last instruction happens to be a read, for which the instruction dispatcher will generate a read command. And this read command basically helps us fetch data from a specific column in the row that we just opened with the activate command. And we also receive some data from the DRAM module. This received data is collected by the DDR5 module and sent back to the host machine through the read capture module that we have on the FPGA. And on the host machine, we can analyze this data to see whether it is the data we expect or whether it has some errors due to, let's say, violating timing parameters or not refreshing in time. So like we can basically conduct various other experiments and like check for bit flips and try to understand why those bit flips occur or not. Okay, so this is basically how the hardware operates. So besides these like main units for like the core operation of the Softmc hardware, there are also like two, I would say, less important modules to enable auto refresh. So this is when the user does not want to issue refreshes manually, but wants to lead this like work of periodically issuing refresh commands to the Softmc hardware. And there's also a calibration controller that deals with some signal integrity issues at the DDR5. So it just issues some other periodic commands to ensure data integrity on the bus. Using Softmc in the original paper, we implement two use cases. First, we perform a retention time distribution study in order to validate the correctness of our infrastructure. Second, we evaluate two latency reduction mechanisms, which were recently proposed at that time. And these two, and we show that Softmc is effective in validating or refuting the recently proposed ideas. Okay, so let's go over these two use cases one by one. Retention time of a DRAM cell is defined as the interval during which the data can correctly store its, the cell can correctly store its data. In this test, we experimentally analyzed the retention time distribution of 3 DRAM modules from 3 different vendors. Here I show how we perform the test using Softmc, or try to illustrate it. First, we write the reference data to a DRAM row. So this reference data pattern could be anything. So let's assume that it's just all the ones. Then we wait for some time. Okay, so first let me tell you that writing the data pattern to an entire row, meaning like writing data to all the columns of a row, can be done with only the 12 instructions or the 12 lines of code that is shown here. So after writing this reference data to the row, we wait for like some refresh interval. So this is not like any refresh interval for the like datasheet dictated by the datasheet, but just anything that we would like to experiment with. So after this refresh interval, which could be like seconds instead of like the typically 64 millisecond refresh, we read the data back. And then we check for the errors in the data that we read back from the DRAM. We repeat the same experiment, but by increasing the refresh interval here that we use in step 2, and repeat the experiment until we like see bunch of bit flips and like collect the basically like understand how many cells fail at which refresh intervals. So this entire program can be implemented with just 100 lines of C++ code. And now I will show you the results.
Hassan,
yes.
Sorry, I have a question about this one. So it's really good that you can implement this testing routine, all of it with more or less 100 lines of code. I guess there are prior work that do similar studies about retention time distribution of in DRAM chips. Do you have a number or basically how does the effort involved in those works compare to doing a study with Softmc?
Yeah. Okay, let me try to remember. So at the time when we developed this tool, there were some commercial products that you can just use very simply. You just plug your DRAM and then press a button, it starts analyzing the DRAM modules for like a set of fixed refresh periods, if I believe, and like reports you back the number of errors or the error rate. Beside that, there were some other experimental platforms. I think one of them I remember was based on the memory controller that Xilinx provides as part of their FPGA software, FPGA programming software. And there to implement a retention time experiment similar to this, you basically need to modify Verilog code, which I would say is much more difficult than changing a few lines of C++ code. So yeah, at that time, I don't think there were like any other like available, like publicly available at least tools that you can easily do such experiments.
Yeah, that makes sense. I guess the commercial tool also uses fixed intervals, which is something you cannot really program.
Well, yeah, I don't remember exactly. Maybe they provide some like configurability. Yeah, in that case, yeah, using those tools is like very easy, but yeah, you don't have like control on those, right? So these are really limited to just that particular study.
Exactly.
Yeah.
And potentially expensive.
Sure.
Yeah. Okay, thanks.
Okay, so now let's look at the results that we obtained from these experiments. So here, and this plot shows for the 3 modules that we analyzed, the refresh interval and the number of erroneous bytes that we observed in these experiments. And these experiments were conducted at room temperature, roughly 20 degrees Celsius. Yeah, so like different lines here represent different modules. So like, for example, just to like give you an idea, like how strong majority of DRAM cells are in today's DRAM chips. compared to like default refresh rates of 64 milliseconds. So even with 8 seconds of refresh interval, like we get only about 8K, like for module A at least. So it is close to 8K bytes that contain bit flips. And so like this is very small considering like typical DRAM capacities that we have today, which are like in the order of gigabytes. So yeah, as I mentioned initially, the reason why we did this experiment is to validate the correctness of our infrastructure, and these results match the results previously reported by prior work, and we conclude that this validates the correctness of our Softmc infrastructure. Okay, moving on to the second use case.
Hassan, I have a question on the previous slide. You say this is 20 degrees Celsius in room temperature. Do you know what the temperature is around the DRAM chip or on the DRAM chip?
Yeah, so I don't remember that exactly, but I would guess it's not like too high. Mm-hmm. First, because like this DRAM was like working on a sort of like relatively isolated enclosure, yeah, meaning it was not exposed to any like heating source, such as like a CPU fan you would have like on a typical like computer cases. And the second reason is DRAM is not heating that much by itself, especially like when it is not operating at a very high intensity. So yeah, so I don't have the exact number, but I would guess like it's not too high, maybe like 30 up to 40 degrees Celsius. Nice.
Yeah, that makes sense given the error rates you're seeing at these refresh intervals, for sure. Yeah. Okay, and I assume, I mean, maybe you didn't repeat these experiments at, let's say, the closer to the maximum temperature point that DRAMs are slated to support, but the curves, I assume, shift to the left, right?
That's true, yeah. As the temperature increases, we expect to see more errors. Mm-hmm. Yeah, we didn't do like temperature sensitivity study for this work, but there are like many other works that do that. Both like published before Softmc and also works that use Softmc to analyze more recent modules.
Okay, yeah, that makes sense.
But then your conclusion that DRAM chips are very much robust is based on the fact that you are not seeing so many errors at room temperature. But maybe the numbers that the vendors are reporting, they are for the highest temperature. And at that point, they are not as robust as you see them in this graph, right?
So we are comparing results from prior work at the same temperature or similar temperature.
Well, yeah, I mean, one of the conclusions from this graph could be that your refresh interval need not to be as small as the vendors are asking you to make it. But then probably they are asking you to keep it 64 milliseconds because they are assuming you might be operating your chips at much higher temperature than room temperature. Sure,
yeah, that's true. So there are many factors. It's not only this. So basically, the intensity, like how often we access a particular row, may also affect the retention time of a DRAM cell. And also, not all DRAM cells are similar, right? So like for like, let's say a handful of rows, it might be necessary to do 64 millisecond refresh even at relatively low temperatures. Yes, so temperature is one reason, but there are many other factors that necessitate, let's say, 64 millisecond refresh to cover all corner cases and worst cases. Mm-hmm. But still, like if you know that your module is operating at low temperature, there is like an opportunity to lower the refresh rate, for example, sure, if you can control that properly. Yeah, so in fact, that is done today, right? So like there are different refresh periods defined even in the DRAM data sheets, depending on the temperature, on the operating temperature. So in particular, there's a like range of like, I think something like 0 to 85 degrees, which is like the normal temperature range. And the refresh periods there will be either 64 or 32 milliseconds. And between 85 degrees to 95 degrees, it is recommended to halve that refresh period to 32 or 16, depending on what was the normal operating range. So yeah, so temperature-based adjustments are already there.
Sure. Thanks.
Sure.
Yeah, it is true, Hassan, but maybe not as aggressively. They're not as aggressive as what this data suggests, right?
True. Yeah, that's for sure.
Yeah, just to give some perspective. I mean, you mentioned this, but can you put some quantify how many bytes are there in, let's say, these modules? So at maximum, you see, let's say, close to 8,000 erroneous bytes. But how many bytes are there in a given module?
Yeah. Okay, so that is a bit difficult for me to remember. So I will have a guess here, right?
Okay.
So these were DDR3 modules. And back then, I think these should be either 2 gigabyte modules or 4 gigabyte modules.
Okay.
Or it could be even 1 gigabyte. So like, I would guess like between 1 to 4 gigabytes.
Mm-hmm. So this is a very small fraction, basically, that's erroneous.
Right. So yeah, regardless, it's a very small fraction. Like even if this was like 512 megabyte module, which I don't believe so, but even in that case, or even smaller, right? So like even this is just 1 megabyte module, even then this is a relatively small fraction of errors that you get with 8 seconds.
Sure. Okay, I mean, that's not the purpose of your study, of course, but it's good to discuss.
Sure. Okay, now moving on to the second use case. So here we analyzed two mechanisms proposed in 2014 and 2016 called NUAT and charge cache. The key idea of both of these mechanisms is that highly charged cell can be accessed with low latency. And the reason is basically like when you consider the time period of 64 milliseconds, the typical refresh period, there's a difference of charge in a cell at the beginning of the 64 millisecond when the cell is just refreshed and at the end of it. And in order to ensure reliable access, manufacturers would have to adjust their timings to ensure that even at the end of the 64 milliseconds where the cell is just to be refreshed, so potentially it contains just enough charge to be able to operate correctly. Yeah, but basically that's the worst case, and the manufacturers will need to tune their parameters according to this worst case. But what if you know that the cells you are accessing were just refreshed? So this is an opportunity where you can potentially reduce the timing parameters and still be able to access the data reliably by exploiting this high amount of charge available in the cells. Here's an example that illustrates that what I just explained. Okay, so here, let's assume that this DRAM cell here initially is at a fully charged state, right? So as as the refresh period of 64 milliseconds continues and close to the at the end of this 64 millisecond refresh period, the cell will contain the minimum amount of charge potentially that can provide reliable access. This is not true for all cells. In fact, many cells may not leak any considerable amount of charge, but still, assuming the worst case, this is what should happen, right? At the end of the 64 millisecond, you should have just barely enough charge. And yeah, basically, if you know that this DRAM cell is fully charged, we can potentially reduce these two timing parameters that we previously discussed, the ready-to-access latency and activation latency, and still be able to reliably access this DRAM cell. And here's the program, the Softmc program that we developed in order to test this idea. We started a step similar to the retention time distribution study where we initialize reference data. But here, instead of initializing the entire row, we are initializing only the single column that we are going to test. And it is because we are testing columns one by one. Then we wait for some interval. And this is basically this interval determines how much we let the DRAM cell leak its charge without being refreshed. So yeah, we don't issue any refresh commands here in this experiment, right? So if you wait longer here, we'll let the DRAM cell leak more of its charge. And for shorter wait times, or shorter intervals, the DRAM cell does not leak too much charge, and it remains at higher cell charge state. And after that, we read back the data, and we do this with custom ready-to-access latency parameters. So this is the time difference between the activate command and the read command, right? So basically, here in this write step, we have activate, write, and precharge. And then when the row is precharged, we wait for some time, and then we activate, read, and precharge again. And the timing here between the activate and read is custom. We tune it to like test with different parameters at like for different iterations of this experiment. And as the next step, we check for bit flips or errors. And we repeat the experiment with different wait intervals and also different ready-to-access latency parameters. Okay, and yeah, so just to give you an idea of like the programming effort required here, our version of this code was implemented with about 150 lines of code.
So I have a question about this experiment. Maybe you will talk about it, but anyways, the second step where you wait for the wait interval or cells to leak charge, given that there's like a distribution of different retention times across the whole DRAM chip, some cells might leak more charge than others, and that could affect the results you get in step 4 where you observe errors. Is that true, or or did you account for that in the experiment, or does it change anything?
Yeah, so yes, that's true. Okay, so let's talk about it over an example. So let's say here for the shorter wait time, we have 1 second, and for the longer wait time, we have 10 seconds. There will be multiple cases. The first case is the cell leaks too much charge even with 1 second, right? And then we get an error regardless of whether we use the short or long wait time. So this data is not useful in this experiment in any ways, at least if we keep the wait times as 1 second and 10 seconds. But there will be cells that will not fail when using the shorter wait time of 1 second. Not fail when using the longer wait time of 10 seconds, right? With a fixed ready-to-access parameter. But the same cell may fail when using a small ready-to-access timing parameter, but may not fail when using a large one. Okay, so I guess that's a bit difficult to explain.
I think I understand it, but basically you filter out the cells that you cannot reliably perform the custom ready-to-access parameter, the different custom ready-to-access parameters on.
Yes.
That's what I understand. I see.
Yes, yeah, we filter out data that is not useful to like in the analysis, and just you use data that is useful, and basically data of cells where they sometimes fail and sometimes do not.
Yeah, makes sense. Okay.
Yeah, we filter out specifically those two cases where a cell always fails or a cell never fails. These are not useful for the analysis. But of course, we can make every cell sometimes fail and sometimes not by tuning those two parameters, right? The wait interval and the latency here. So this is why it is important to repeat this experiment with many different configurations.
You can find the range where the cell doesn't fail from retention, charge leakage by adjusting the wait interval.
Right.
Yeah. Okay.
Okay, so before I show the actual results, I would like to discuss what the results should look like based on what the expected results should look like based on the idea that is proposed in the two papers that we mentioned previously. So here on the x-axis, we show the refresh interval, and y-axis is again the number of bytes with at least one error. So what we see here is that, let's say we look at the right-hand side of this plot, right? So here what we see at large refresh intervals where we let the cells leak a lot of charge, we see that by using small radio-to-access latency, let's say of 3 cycles, we get a lot of bit flips, right? We get a lot of bytes with errors. But when we use a larger timing parameter, let's say a 6, then we get like very few errors at this point of the plot. And if you look at a bit closer to like more realistic refresh intervals, like smaller refresh intervals, then the difference between like these different latencies like become smaller, and then like even cells even when using small radio-to-access latency parameters such as 3, 4, and 5, here 6 is the default, by the way, like the data sheet value. Even when we use small timing parameters, we can still reliably access the cell. Okay, but like as we leak more charge, then the effect of reducing the timing parameters is bigger, and then the probability of accessing with lower timing parameters causing an error is much higher. And yeah, this is what we expect from the idea, right? So like when the charge is high, meaning when the refresh interval is low, we expect to be able to access the cell even with low timing parameters. Now let's look at the actual results. So these are the real curves that we get from the analysis of, I guess this is, again, data averaged across the 3 modules that we analyze in this work. So here again, we see radio-to-access latency as like in terms of like DRAM cycles, 6, 5, 4, and 3. And this experiment was conducted at 80 degrees temperature. So as opposed to the expected curves here, what we see is much different. So first, we see that like regardless of the timing parameters used, the curves are sort of like very similar and they overlap here, right? Sure, as we increase the wait interval or the refresh interval, the number of errors increase, and this is expected, but we don't see divergence across these curves. That should happen if cells with higher charge can be accessed with lower timing parameters. And the second observation here we have is with very low latencies, such as 3 cycles, it is not possible to access the cell reliably, even at like very short wait intervals. So here, I guess the lowest point here we show is 8 milliseconds, but we tried with even lower. We tried with 1 millisecond, and like I guess we tried with the smallest we can. So even if when you access this cell again right after refreshing it, it still does not always return the correct data. Okay, and from this, we basically do not observe the expected latency reduction effect of the idea proposed in these prior works. We tried to understand the reasons. And one reason we found is that the memory controller cannot externally control all timing parameters or like all the operations that happen inside the DRAM chip. And let me explain one of the operations where the memory controller and thus Softmc does not have control on. So let's assume initially we have a cell and sense amplifier at these charge levels, right? So like the charge of the DRAM cell is in the region of data 1, and sense amplifier is in pre-charge state. So it's like it's between data 1 and data 2 levels. And here, this pink line represents the radio access charge level. And after activation, the goal is to make the sense amplifier reach this charge level, so the read and write operations can happen. So once we issue the activate command, charge sharing between the cell and sense amplifier begins. And after charge sharing completes, which is roughly this point, the sense amplifier must be enabled. And this operation, enabling the sense amplifier, is what memory controllers does not have control on, right? So like this is a fixed latency that is controlled by internal like DRAM circuit. And yeah, after the sense amplifier is enabled, the sense amplifier charge level reaches these radio access level, after which we can, the memory controller issues the read and write commands. So we argue that if somehow the memory controller got a control over this parameter, perhaps it would have been possible to exploit the idea that was proposed in prior work by changing this internal fixed latency. So yeah, here our hypothesis is that maybe like the potential for reducing the timing parameter is within this fixed latency that's internally controlled. Yeah, and here is like the potential reduction here show illustrated here based on the sense amplifier reaching the same level as in the blue curves.
So Hassan, I have a question here. I think this explanation is nice. It basically shows why in practice what you observe doesn't match the theory, right? Theoretically, what we should observe. But it also points to something that is interesting, I think. If somehow these latencies that you mention are not fixed, but made controllable by the memory controller, perhaps you can get the benefits that are expected from theory that prior works proposed, right?
Yeah, definitely. Okay. I agree with that.
Okay, how do you, can you guess how feasible that would be, or how expensive that would be?
Yeah, let's see. So doing this, okay, so we activate the entire row at once, right? So like this control is like per like row activation. So all sense amplifiers in the row that like are connected to different cells have to be activated at the same time. So this can be done via a, let's say some like mod register in DRAM, where the memory controller like adjusts this configuration in advance, like prior to activating the row. Yeah, I think that may work, but yeah, the memory controller then needs to like manage that as well, right? So like when accessing a row that cannot, a row that has like very weak cells, where this like where there's like not potential for reduction, then it should switch back to using the default timing parameters.
Yeah, certainly the memory controller needs to characterize and figure out which cells or which rows it could do this on, right?
Right.
Yeah. Yeah.
But if it needs to change this parameter for every row, then it might be significant overhead. Like you are adding an additional command between activation and read.
Yeah, that's true, but that may not necessarily translate to a high overhead. And the reason is, yeah, there are like a lot of opportunities to hide the latency of the like individual commands, right? So like while waiting for let's say activation in one bank, the memory controller can issue this command to change the configuration of another bank. Yeah, that's one reason. Another reason is it may not be necessary actually to change that parameter that often, depending on what is the profiling result, right? So like what a fraction of DRAM rows can be accessed with low latency and what fraction cannot. So if it's like, yeah, 50% of the rows can and 50% cannot, and if your access pattern is like random, sure, yeah, you may need to switch back and forth between low latency and high latency modes.
Yeah.
But yeah, I guess it depends on the implementation and like the DRAM characteristics.
Yeah, how aggressive you want to go.
Right. And then what I mentioned is not the only way of like exploiting this idea. There might be other ways that I cannot think of right now that might be more efficient to implement and operate.
Yeah, one thing that comes to my mind is I think Loise's codic substrate can be used for this purpose also, right?
Right.
That propose let's say programmable latencies, let's say, yeah, or more fine-grained control over internal DRAM timings. And it does it at low cost, so I think it could be a use case for that.
True. Yeah.
Okay.
Yeah, so these were basically the two use cases that we analyzed in this work in 2017. But after we published Softmc, or like even before it was published, there were like other research that was enabled or other research that took advantage of Softmc. And here's a list of these other publications here, I guess, ordered chronologically. And these are the research enabled by Softmc from our group, from the Safari. Here, I would like to specifically mention Trespass because it is related to the second contribution, which I will talk about shortly. In Trespass, we show for the first time how to bypass RowHammer protection mechanisms implemented inside current DRAM chips, where the manufacturers at some point claim that their chips are secure against RowHammer. So we basically show that, that's not true. And with specific access patterns, it is still possible to cause RowHammer bootflips on those modules. So there are also publications that use Softmc by other research groups. And here's a list of those words. Okay, I would like to summarize this contribution. Softmc is the first publicly available DRAM characterization infrastructure. It is flexible and easy to use. We have this source code released on GitHub, and you can access it through this link. And Softmc enables many new studies, ideas, and methodologies in the design of future memory systems. Okay, and now moving on to the second contribution. Yes,
before we do that, I have a question about how to use the Softmc API to generate the DRAM command. So let's say, and basically the question is how much time it takes to convert a high-level statement into a DRAM command. For example, if my first statement says that I want to generate an activate signal, and the next says I want to wait for 10 nanoseconds, and the next states that now I want to generate an activate, first activate and then read. So if the time to generate the second command itself takes 20 nanoseconds, then I'm certainly going to wait for at least 20 nanoseconds, not 10 nanoseconds. And I'm just looking at these numbers. Is that correct, or you never really experienced this kind of?
So that we don't experience that latency, and the reason is, okay, so maybe I will go to that slide very quickly. So here, right, so like I sort of explained that, wait, why is this not animated? Okay, so here, like once the host machine generates all these commands, right? So like, remember that C++ code that I showed? So that like prepares the entire program, and all these instructions are sent and buffered and ready to execute, and they wait in the hardware.
Okay, and then are they DRAM commands or are they still host C++ instructions?
Well, these are sort of, let's say, no.
At some point, I need to convert them from C++ statements to DRAM commands, right?
No. So yeah, we don't set C++ code to the FPGA. So okay, well, what happens is here, these functions basically generate a binary data of like 32 bits each, and these 32 bits represent a instruction that will be executed by the Softmc hardware. Okay, those instructions are simple. Decoding them like in hardware takes like no time. Like an essential like this is a like pipeline hardware structure, and like decoding these instructions and converting them to DRAM commands like is like all pipeline takes one cycle in each pipeline stage.
Okay.
So like between these commands, there's like no additional latency.
Sure.
Yeah. So okay, yeah, maybe I will use this to mention one limitation. So like I said that here we buffer the commands and start executing once the instruction queue receives all the commands, right? But what if the number of commands is, or the number of instructions here is too large to fit into the instruction queue, because like it's a hardware structure which has limited size, right? So that's one limitation of the tool. So I think here we have space in this first prototype. We had space for 8K instructions. So like, yeah, if your program is bigger than 8K instructions, then you need to split it into multiple programs, multiple smaller programs. And there you have the problem of the PCIe latency, because like, yeah, between like the execution of two programs, there will be the PCI Express delay, which is in order of microseconds. So you have to split your program intelligently to.
And you can't write this buffer partially, like once you know half of this is empty, you get but anyhow the latency is still very high.
Yeah, it doesn't work that way.
Yeah.
But you solve this problem in the second version of Softmc that is not released yet. But there, like instead of like this fashion of producing and consuming these instructions, we changed this part to be more like a simple CPU core, where you have a small instruction memory, right? Where you have like control flow instructions as well, such as like jumps and like branches, where we can create loops where like one instruction is like executed multiple times within that control flow. Right?
Okay.
Yeah. So here it is like sort of a trace of instructions. Yeah. Exactly.
Yeah.
So yeah, we sort of enable like executing longer and larger programs by doing that. Okay.
Cool. Thanks. Just a small comment. Are all of the remaining three work that you are going to explain, they use Softmc or not?
Well, indirectly, yes. So like Softmc helped with developing some understanding about like the operation of these DRAM modules that like eventually like helped us design those ideas, or like have intuition about them, whether they will work or not. But we don't necessarily use Softmc or like any data generated by Softmc in these works. But in the second contribution, U-TRR, we do. So here we use Softmc directly.
So Hassan, before you move on, first I'll make a comment and ask another question.
Okay.
Can you go to those works that are enabled by Softmc? Because I think a couple of them answer the earlier question that I asked, which we briefly discussed, which was on violating the timing parameters, right? I think some of these works showed that by violating the timing parameters, you can generate true random numbers and also physical unclonable functions, right?
True.
And maybe others also. Like QuarkTRNG does that, right? D-range does that, generates true random numbers by violating the timing, or maybe violating the timing parameters to a level and figuring out which cells fail randomly. Yeah. Okay, that was one thing I wanted to point out. I think the other thing is in the next slide, which is also related to this, that compute DRAM work at Micro 2019 does essentially the same thing, right? Violates the timing parameters for a completely different purpose, which is doing copying of rows, and also it shows that you can do row copy and bitwise and then OR by carefully violating the timing parameters in off-the-shelf DRAM chips. Okay, and with that said, I think it's good. One question I have is how easy it is really to use this infrastructure. Clearly, having a C++ model is good, but you still need to go into if you, let's say, if you want to do something different, you still need to go into the guts of the FPGA. Is that not correct?
Well, it depends how different. So we have like a support for pretty much all major DRAM commands. So I guess we don't have support for, let's say, entering and exiting self or fetch mode in DRAM. So if you would like to experiment with that, yes, you need to dig into the Verilog code and make some changes to enable that. But if you like to do some like RowHammer experiments or retention time experiments or violate some timing parameters, these are all possible by just changing the C++ code. And for that, you just need to understand how DRAM is controlled, right? How the memory controller operates. Because essentially what happens with Softmc is that the user replaces the memory controller. But you don't necessarily need to know how Softmc hardware works. You don't need to know about Verilog.
I see. So basically, if the commands, if the experiment you're trying to do is already supported by the instructions you have in Softmc and the commands that are supported, then you don't need to deal with any FPGA internals, let's say.
True.
So you can just program in C++. Of course, you still need to know what you're doing, I guess, with your instructions at an API, right?
Yeah, certainly.
Okay, and the next question is, you kind of covered one limitation of Softmc, but do you foresee other limitations of this version of Softmc?
Yeah, I mean, one obvious limitation was that it supported only DDR3. And even at that time, I guess we had DDR4 modules in the market. So yeah, but that's something we support now in the new version of Softmc. Yeah, so I guess that's one limitation, like support for a more recent type of DRAM modules. Let me see. What else is there besides that? So yeah, I mentioned like the program size. So yeah, if you feel like for some reason need to have like very large programs, that PCIe latency gets in between and you have to manage that somehow. Yeah, I guess these are the two major limitations that I can think of right now.
Okay.
Well, I guess like there are some like other technical details, such as we supported only one rank. So if you like plugged in a dual rank module, you can only work with rank 0. But yeah, those are not as important.
But those can be easily fixed, right? With some effort in the infrastructure. Okay, thanks.
Okay, awesome. Now moving on to the second contribution, U-TRR, which is a new methodology for uncovering or understanding in-DRAM RowHammer protection mechanisms. So very brief explanation of what is RowHammer. So in order to access data from a row here, let's say row 2, the memory controller first opens or activates this row. After all requests are serviced from row 2, the memory controller must close or pre-charge this row. So like this is like the activate and pre-charge commands that we already discussed. So if these operations, the activate and pre-charge, happen like back to back and rapidly for like thousands and millions of times, due to increasing cell-to-cell interference between cells of these neighbor rows, there's a chance that the cells in row 1 and row 3 will leak too much charge and experience bit flips. And like as we continue to open and close row 2 or hammer it, there's a chance that even more errors will happen, even errors in rows that are further away from the row that we hammer. So basically, RowHammer is like about repeatedly activating and pre-charging a DRAM row to interfere with the other rows or cells in the neighbor rows and cause bit flips in them. So here's some like terminology that we use. We call the row that we hammer an aggressor row, and the neighbor rows that we can affect are victim rows. To protect their DRAM chips against RowHammer, DRAM vendors currently implement proprietary RowHammer mitigation mechanisms typically known as target row refresh, or TRR. So TRR is an umbrella term for different types of RowHammer protection mechanisms implemented in DRAM chips today. So even the same vendor sometimes implemented different TRR mechanisms across like different generations of their DRAM chips. But their key idea is roughly the same. So TRR refreshes nearby rows upon detecting an aggressor row. But how the aggressor row is detected and when the nearby rows are refreshed, so that depends on the particular implementation of the TRR mechanism. So let me demonstrate how TRR operates at a high level. So here we have a TRR-equipped DRAM chip. Let's say we activate row 2 and rapidly open and close it, or like hammer it. And let's assume at some point the TRR mechanism detects this row 2 as an aggressor row. Then the memory controller, the TRR unit here waits for a refresh command from the memory controller. These are the refresh commands that the memory controller periodically chooses to perform regular refresh, not necessarily or even not to do anything with RowHammer, or that was the case in the past. But in these current DRAM chips, the TRR mechanism takes advantage of the slack time available in the refresh latency to also perform RowHammer mitigation. So meaning here, some refresh commands will perform regular refresh as in conventional DRAM, but some refreshes will also perform neighbor row refresh on detecting an aggressor row, as in the example here. And we call these refresh operations TRR-induced refresh to differentiate them from regular refreshes that happen periodically and usually they follow a particular order. Okay, so what is the problem with TRR? Although we know how TRR operates at a high level, different vendors implement TRR differently, and the exact operation of these TRR mechanisms is unknown. And this is a problem because TRR is because we cannot easily study the security properties of TRR and make sure TRR is secure. So the goal of this study is to study in-DRAM TRR mechanisms to understand how they operate, assess their security, and secure DRAM completely against RowHammer. And to this end, we propose U-TRR, which is a new methodology to uncover the inner workings of TRR. And the key idea of TRR is to use data retention failures as a side channel to detect when a certain row is refreshed by TRR. I will try to explain this with an example in the following slide, not this one, but the next one. So U-TRR has two main components, row scout and TRR analyzer. The first component is used to find a set of DRAM rows that meet certain criteria needed by the second tool, TRR analyzer. And this row scout basically identifies a set of DRAM rows and their retention times. So the requirements here are such as like these rows should have similar retention times, because we usually want to see like all of them fail or not fail at the same time, depending on which one is refreshed. And other typical requirements are they should be close to each other, or they should be one row apart, because we want to place an aggressor row between two victim rows. Yeah, so basically this row scout tool profiles the retention times of the rows and provides useful set of DRAM rows to the second component. And the second component is the main component that performs experiments with different parameters to understand when TRR-induced refreshes are produced and which exact rows they target, and when these neighbor row refreshes happen. And yeah, using these two tools, basically a user can perform experiments and analyze when TRR-induced refreshes happen or not, and build an understanding of the underlying TRR mechanism. So here's an example, like I would say toy experiment, to illustrate how a typical U-TRR experiment works. Initially, U-TRR identifies a set of DRAM rows that have similar retention times. So let's assume retention times of rows 0, 1, and 2 are T. And so like at the end of this timeline here, we expect all the cells to fail, or all the rows to fail. But in this diagram, we represents the weakest cell in each row with those circles, right? So like we essentially monitor only the weakest cells in each of the 3 rows. At time 0, U-TRR initializes the rows with, let's say, all ones. If these 2 rows remain closed and not get refreshed for T, we expect the weakest cells to lose a significant portion of their charge, and as a result, we observe retention failures at time T. However, if any of the rows get refreshed, for example, when we issue a refresh command at T over 2, the refreshed row should remain correct at time T. To test when the TRR mechanism selects which rows to refresh, we perform multiple experiments where we change the number of times an aggressor row is hammered. For example, activating row 1 5 times may not make the TRR mechanism refresh any of the neighbors. However, activating row 100 times may trigger neighbor row refresh. So in this case, the TRR mechanism detects row 1 as an aggressor row. And how we observe that TRR happened is basically at time T, instead of retention failures, we see retention success. We can also say that this might be due to regular refresh, but filtering out retention success due to regular refresh is easy because it always happens at a specific order, right? So like, let's say at every specific command in an 8K refresh command window, we'll refresh a particular row. Okay, so like at that particular refresh, we already know which row will be refreshed by regular refresh. But if we also observe retention success on other rows, we can say that these are due to TRR-induced refresh operations. And this is simply how our methodology works. So we repeat these experiments with like various number of aggressor rows by hammering them in different orders and with different times, and try to understand when a TRR mechanism detects an aggressor row and when it does not detect an aggressor row. Yeah, and we perform many of these experiments to understand the operation of different TRR mechanisms. So here's how we implement U-TRR. We use Softmc, the version modified to support DDR4 DRAM modules. And this is like another picture of the board that we use, again, with a temperature controller that helps us to perform the test at stable temperature. We use Softmc because it provides fine-grained control over DRAM commands, timing parameters, and temperature. In this work, we analyzed 4 to 5 DDR4 DRAM modules from 3 different vendors. So we have a table 1 in the paper that lists some, sort of summarizes our observations and the organization and other like information related to the modules. I'll get back to this table and explain some of the columns in more detail once I explain some of the results that we have in more detail. So let's look at the TRR mechanism implemented in modules of vendor A. We observe that there are 2, or I guess in total 3 types of refresh commands: regular refresh that every DRAM module does, and also TRR capable refresh. Here, this operates in 2 modes that we call TRF1 and TRF2. And I will explain the difference between 2, but let me explain how these commands are scheduled, or how these 2 operations are scheduled. So here, each tick in this timeline represents a refresh command that the memory controller issues with fixed time intervals. The first 8 refresh commands are used to perform only regular refresh. And then the next refresh command is used to perform TRF1. And the next 8 refresh commands are again for regular refresh, and the following refreshes for TRF2. And this repeats in this way, basically 8 regular refreshes, 1 TRR capable refresh, interleaving TRF1 and TRF2. And we also observe that this particular TRR mechanism tracks potentially aggressor rows using a counter table with 16 entries. And the counter table looks something like this, where there's a row ID. This is the row ID of the potential aggressor row, and some counter that represents how aggressively this row was hammered in the past. So what's the difference between TRF1 and TRF2? So you notice that TRF1 refreshes the victims of row ID with the largest counter value in this table. Okay, so yeah, this is quite intuitive. So like whichever row was hammered the most, it is the one whose neighbors will be refreshed first. But TRF2 is a bit different. So instead of like, yeah, it basically has nothing to do with the counter value, but it basically iterates over these different entries one by one and refreshes the rows that this TRF2 pointer sort of points to. Okay, so like in this particular instance of TRF2, let's say this second entry, the neighbors of the second entry are refreshed. The next TRF2, after how many? I guess 20 commands, will refresh the third entry in this counter table. Okay, yeah, and this is the difference between TRF1 and TRF2. Okay, so knowing all this, we figured out that we can actually bypass this protection mechanism. And the approach is to ensure that an aggressor row is discarded from the counter table prior to a refresh command. And achieving that is pretty simple because we know, because the counter table has limited capacity, and then we know that that capacity is 16 rows. So following a refresh command, which could be either like regular refresh TRF1 or TRF2, we start by refreshing two aggressor rows, A1 and A2. So these are the actual aggressor rows that we would like to hammer and cause bit flips in their neighbor rows. The reason we hammer two aggressor rows here is to amplify the effect of, so this is basically called double-sided RowHammer attack, where you hammer the rows on both sides of a victim row. Right? So like that sandwiched victim row is being disturbed more by getting both of its neighbor rows hammered. So we hammer A1 and A2 n times. Then we continue by hammering 16 other random rows. We call them dummy rows that are like not victim rows or aggressor rows that we use in this experiment, right? So like these are just rows in the same bank, but somewhere else. And we make sure to activate each of these dummy rows n+1 times, one more time than the actual aggressor rows. And this basically what causes the A1 and A2, which were initially in the table at the time when we activated them, to be discarded from the table, because the table like prioritizes the rows that were activated more and keeps them and discards A1 and A2. And when the memory controller issues a refresh command, even if this refresh command performs TRF1 or TRF2, doesn't matter. It never refreshes the neighbors of A1 and A2 because A1 and A2 are not in the table. And this is how we bypass this particular TRR mechanism. One like sort of difficulty here is that the attacker needs to synchronize accesses with refresh commands. Although this is like sort of a difficulty, this is not impossible. In fact, it is shown that even with a JavaScript code, you can understand when refresh commands are issued by essentially using a timing side channel by analyzing how long it takes for your memory requests to be serviced. And then when there's a latency spike, you can attribute that to a refresh happening. Yeah, and we conclude that circumventing vendor ASTR by discarding the actual aggressor rows from the counter table is possible.
Hassan, one question.
Mm-hmm.
What is the policy of inserting a new row in this table? So how do you know that there is a row that I want to insert in it?
Yeah, so we observe that the row with the smallest counter value is discarded.
But how do you know that this is the time to insert a new row in?
Yeah,
so do you monitor all the rows and take one of them and put in this table when it crosses the threshold?
Yeah, so like for the TRR mechanism, there's like no way of knowing that, right? So let's say we are at here demo row 16 and we activate demo row 16 for the first time. It is not in the table, meaning yeah, we don't know how many times it was activated in the past.
Exactly.
So the TR mechanism thinks that, yeah, I should replace the smallest entry here in the table with this one. Because like, yeah, this might be the new aggressor row. And I should keep track of that instead of the other two rows that were not accessed recently. And their counter values are low.
Okay, so apart from this table, there is a counter somewhere else also that tracks some of the rows that are not in the table to mark them as candidate for inserting into the table.
Yeah, so like there was a paper called Graphene that was proposed in, I guess, I don't remember the conference, but I guess it was in 2020. So there they proposed like a similar counter-based mechanism, and they call that additional counter that you mentioned a spillover counter. That spillover counter basically indicates the maximum activation count of a row that's not in the counter table. So when you insert a new row to the counter table, its counter value becomes equal to the spillover counter plus one. But that is like, as you can get, a like approximation, right? So like that's not a perfect way. So you can keep track of like rows that are activated. So you can basically keep track of like 16 rows that are activated the most. But if there's a row that is like not activated as much, but close, you cannot keep track of that. Okay, should I move on?
So does that also mean that if you had enough counters with that algorithm, you could potentially prevent any attack?
Yeah, sure. Yeah, I mean, if you have like infinite number of entries here, or number of entries equal to the number of rows you have in a bank, yeah, I guess this mechanism will work, but that's not feasible.
Yeah, I guess. There's a lot of storage to put in the DRAM chips.
Right. So the goal is really to find a way to do this very efficiently with like lowest overhead possible. And this is like, let's say, relatively low overhead, but as we show, it is not secure if you know like how this mechanism works. Okay, so I want to cover different modules of different renders one by one, but maybe again we can look at the table that I mentioned to like see a summary of these different mechanisms. Leveraging the understanding we developed using U-TRR, we craft new RowHammer access patterns that circumvent the TRR mechanisms of the three major DRAM vendors. We evaluate the effectiveness of these patterns that we developed on the 45 DDR4 DRAM modules, and we find that the new RowHammer access patterns cause a large number of RowHammer bit flips. So let's look at those like results on the effectiveness of the new RowHammer access patterns at DRAM row granularity. So here we show the number of, or the percentage of vulnerable DRAM rows, meaning here like a DRAM row with even one bit flip, we consider that as a vulnerable DRAM row. And we show bars individually for each of the 45 modules. We make several observations. First, all 45 modules we tested are vulnerable to our new RowHammer access patterns. There wasn't a module across these 45 modules where we cannot cause a RowHammer bit flip. For many modules, our RowHammer access patterns cause bit flips in more than 99.9% of the rows, like almost in all rows. But why some modules are less vulnerable? We found three reasons for that. Some modules are just fundamentally less vulnerable to RowHammer. So like their like minimum activation threshold, even without any RowHammer protection, is just higher. So just as an example, there are like modules where they fail, or like we can cause a RowHammer bit flip by hammering two aggressor rows in like dual-sided manner 10K times each. But there are also modules where we need to hammer each of these aggressor rows 100 times each, right? So like there's like 10x difference. Second reason for low percentage of vulnerable DRAM rows is that these are different trial mechanisms where we maybe did not tune our access patterns to perfectly exploit the TRR mechanism implemented in these modules. And the third reason is unique co-organization we observed in some modules of vendor C. So here we observed some sort of a shielding effect. So this is probably some sort of a RowHammer mitigation technique implemented at circuit level in DRAM chips. In these modules, when we hammer one row, we observe that we cannot sometimes cause RowHammer bit flips on both sides, on like both victims of this row, but only on one victim. And this was like consistent typically across the entire module. And yeah, you think that that might be because of some circuit level mitigations implemented in this DRAM chip. But we conclude that although some modules are less vulnerable, our access patterns successfully circumvent the TRR implementations of all three DRAM vendors. And yeah, being able to cause even one bit flip is in most cases sufficient to launch a system level attack. We have other observations and results in the paper.
Hassan, one question.
Sure.
So you just mentioned that for some aggressors, you can only incur victims on like one side of the victim row, right? And you said that it's like a circuit level mitigation. Could you elaborate on it more? Like what kind of mitigation is it, or could it be like some sort of row address remapping that causes this? Maybe like that other victim row is like very, very far away, but yeah.
Yeah, so we looked into that. So initially we thought it's a row remapping, like some address scrambling issue that we are facing. But it turned out it is not. And the reason is, so there is a still slight effect that we get from the, so let me try to explain it here by a little drawing. If I can first open up some space in the slide. Okay, so I will try to draw an aggressor row here and a second aggressor row here. So these lines represent the row, right? And here we have the victim row. So what we observed was, yeah, if you do a single-sided RowHammer, hammering only this aggressor row or only this aggressor row, only one of the aggressor rows will cause a RowHammer bit flip. And yeah, this is the shielding effect that I was talking about. We don't know exactly what it is and how they implemented it, but like this is what we observed. But how we like made sure that this is not an address scrambling issue is when we perform double-sided attack compared to single-sided attack, we observe that the number of activations we need to do reduces when we do double-sided compared to single-sided. So this basically suggests that, let's say with a single-sided attack, we are able to cause a RowHammer bit flip only using this aggressor row. I don't know like how to, well, I just like circle it one more time. Yeah, only this aggressor row can cause a bit flip in the victim row, single-sided attack. But when we do double-sided attack, that total activation count that we need to perform on the second aggressor reduces. So this is like one thing we observed, but we also, to make sure that still like this is not a address scrambling issue, we also like analyze the entire DRAM bank, right? So after hammering this aggressor row, assuming that it should have a row that maps to its other side, it doesn't necessarily have to be like, let's say if this is row 100, this is row 101, maybe on the other side of this aggressor row, this is mapped to row 200, right? To check this case, if this is possible, we basically looked into all the rows in the DRAM bank, and we didn't observe a bit flip anywhere else in that DRAM bank by hammering this aggressor row A. Does that make sense?
Yeah, thanks, Hassan. So this basically implies that there's some kind of like physical isolation that prevents the other side to have bit flips.
Yeah, yeah. This is what you think. Yeah.
Yeah, thanks.
Okay, cool. Yeah, so we have other observations and results in the paper. We have more observations on the TRR of the 3 vendors. So if you're interested to learn about how these TRR mechanisms work of the other DRAM vendors, I definitely recommend checking out the paper. We have analysis on the effectiveness of ECC against RowHammer access patterns. Basically, ECC can can detect and correct some bit flips, but RowHammer access patterns can cause more bit flips than ECC can correct and detect. And potentially, if the attacker is smart, can work around the detection logic and cause bit flips in particular locations in the ECC code words, where that will translate to bit flips in useful locations in the data to launch a system level attack. So we have detailed description of the crafted access patterns. We have various sensitivity studies. And here's that table again that I mentioned. So we already looked at the modules of vendor A. They all use counter-based RowHammer protection. Their parameters are slightly different. So specifically for 2 modules here, 813 and 14, we observe that instead of refreshing 2 neighbors from each side of an aggressor row, this particular module performs 1 victim row from each side of the aggressor row. So here the reason the number is 2 is 2 victim rows in total, 1 from each side. And here it's 4, 2 victims from each side. And other vendors perform only, well, except some models of vendor B perform again 2 victims from each side, but others do 1 victim from each side. Vendor B performs sampling-based RowHammer detection. And this works by randomly or pseudo-randomly, we don't know exactly the randomness function used here. It samples the activation commands, right? So every activation that the memory controller issues has a chance to be sampled. When it is sampled and when it is a turn to perform a TRR capable refresh, then the TRR mechanism basically refreshes the neighbors of this last sampled row. Here we say that the aggressor capacity is 1 because the sampling capacity is only 1, right? So only the last sampled row is detected as an aggressor row. And let's say you are attacking row A. After attacking row A, if you also attack row A2 and A2 gets sampled over row A, you can basically hide all your activations to the previous row that you attacked, row A in this example. Okay, and yeah, module C is a bit more complicated. So we think it's a sort of a mixture between some random, random seeded counter-based mechanism. And this is why we say it's a mix here. But we also have some other details here in this table, such as the percentage of vulnerable rows. This also was in the plot that I showed earlier. And here's a metric to indicate how vulnerable these modules are. Here we show the maximum number of bits per row per hammer. Yeah, and you can find some other information about the modules here, such as the chip density organization, the count of the count of ranks, banks, and pin count of these chips that are used in these modules. And HC first here, maybe this is important also to explain, is the minimum activation count required per aggressor row in a double-sided attack to be able to cause a bit flip, even without RowHammer protection, right? Without issuing any refreshes. So as you can see, here's a pretty big difference. We have modules here that have 60K to 7K HC first, minimum activation count, but we also have modules that are close to 200K activations, which indicates a significant difference between the vulnerability level of these modules.
So Hassan, I have a question on this. I think it's a very nice table that summarizes a lot of things.
Mm-hmm.
One question is the aggressor capacity of C, you write unknown over here.
Yeah.
Is it unknown because it's very difficult to figure out? Is there's some fundamental reason why it's difficult to figure out, or is it because of some other reason? Maybe you didn't have enough time to examine it.
Yeah, so I guess it is difficult. Yes, we didn't have enough time to examine it, and yeah, we thought it is not necessary because even with the information that we managed to gather, we were able to craft access patterns that will bypass the DRAM, the TRR mechanism implemented in these DRAM modules. But it's unknown because, as I mentioned, there is some randomness in this mechanism. which makes it difficult to understand exactly how many rows this mechanism can keep track of. Definitely, there is a limitation. There has to be some limitation, but because of that randomness, and because we couldn't understand how like that randomness operates, we like don't know which row has a chance to enter like this state of being tracked or not.
Mm-hmm. Yeah, makes sense, I think. So there's some more effort that basically it requires more effort to make that known, let's say.
Yeah.
And I think there's a other thing that is interesting in this table. You get a very high fraction of vulnerable rows, especially for those chips where HC first is low, on the order of 10K or lower, right? Yeah, which makes sense, I think.
Yeah. So basically, yeah, I guess like that helps a lot, right? So like even if when the access pattern does not work perfectly, if HC first is low, this means that like even avoiding the TRR mechanism for a relatively short amount of time is sufficient to cause a bit flips, right? You don't have to avoid it all the time during a refresh period of 64 milliseconds or during the entire RowHammer attack, let's say.
Yeah. So it's basically easier to circumvent the protection mechanisms when the chips are more fundamentally more vulnerable,
right?
Which is going to be the case. Okay.
So yeah, to summarize, the RowHammer vulnerability of DRAM is a critical reliability and security threat. The security guarantees of TRR, which is the commonly used RowHammer protection mechanism, cannot be easily studied as TRR is obscure, undocumented, and proprietary. In this work, our main goal is to answer the following questions. Is TRR fully secure, and can we validate its security guarantees? To this end, we propose U-TRR, a new methodology that leverages data retention failures in DRAM to uncover the inner workings of TRR and study its security. As we just discussed, we analyzed 45 DRAM modules, 15 from each DRAM vendor. Using U-TRR, we crafted new RowHammer access patterns that we show can cause bit flips in all of these 45 DRAM modules. In some modules, these access patterns can cause bit flips in almost any DRAM row. We observe that these access patterns can cause up to 7 RowHammer bit flips in an 8-byte data word, which makes ECC sort of ineffective if the attacker is smart to develop, say, let's say, good and efficient RowHammer attack to like work around the ECC protection. So U-TRR can facilitate the development of new RowHammer attacks and more secure RowHammer protection mechanisms. And this was like all about the second question.
Sorry, Hassan, I have some questions on U-TRR. So first is, because you mentioned ECC, I guess rank level ECC, you can disable it with the Softmc platform, and you're not, in your experiments, you're not really affected by those. But do you think if you were using newer DRAM chips with potentially in DRAM ECC, it will be harder, or basically, what would the effects of in DRAM ECC be on your experiments? Would it render the methodology but probably not useless, but make it harder to do all the analyses?
Definitely it will complicate things. So yeah, that's for sure. And the reason is basically even if when you cause like too many bit flips, more than the ECC can correct and detect, it will still apply the correction or like the decode function, right? The ECC decoding. And yeah, it will just makes things looking not as well. I would say natural, but what I mean that the row bit errors that you cause on the DRAM cell will not translate to errors that you observe after the decoding, right? So like, let's say you can cause 3 bit flips. After the DCC decoding, these may translate to 4 bits or 2 bits, and their locations may change. And so like, these are all difficulties that make practical attacks difficult to run. But still, like after, so it's called templating, right? So like after templating your model, and then you have a location and the data, and you know how it flips, right? So like this is the profiling part, something you do in the profiling part. Then at the system level attack, you can force you can force sensitive data to be placed in this location and still cause a bit flip. So yeah, I guess like what I'm trying to say is, yes, it complicates things, but yeah, it's not a protection.
Okay.
It just gives a hard time to the attacker. But I believe that this is still possible to launch system level attack with those chips with on-die ECC.
And what about if someone wants to use U-TRR and has the Softmc platform? Can they run the methodology as easily if they are using a DRAM ECC chip?
Yeah, I think so. So like the only thing will change is that the observed bit flips will not be the raw bit flips that RowHammer causes. But okay, so I will here refer to Minesh's work, right? He looked into on the ECC and reverse engineered the function behind that. So like, yeah, I would suggest like people look into that to like understand how to sort of reverse engineer how on the ECC works. And basically there's a way to translate those visible like post correction bit flips to raw bit flips to some extent.
Yeah, I guess in the worst case, someone can do that reverse engineering first and then apply U-TRR on top.
Yeah.
In the worst case.
Yeah.
And even then, maybe those on the ECC corrections don't affect the methodology here as much, and they don't even need to do that.
Right. Yeah. I mean, I guess like you don't even need to, yeah, reverse engineer that on the ECC. Yeah, I don't think like raw bit errors are necessarily useful. The first, you don't have control exactly which cell to flip, right? So like this is something you observe after performing a RowHammer attack. Some cells lose too much charge and they flip. So yeah, you are, I guess, more interested in what is observed. So yeah, as long as you can cause bit flips in specific locations, then you can place your data there and then hopefully cause bit flips in the same locations.
I see. Yeah. And my next question is about, again, the methodology here. It's clearly defined how to, I guess, reverse engineer a TRR chip, at least the way you do it. You clearly explain it in the paper. But do you have any pointers for people who would like to, I guess, automate this step? Because I think there's some heavy analysis involved in after observing bit flips and performing the experiments you described.
Yeah. So automating can be a bit difficult, especially like if you have no idea about how the TRR mechanism operates. But it might be easier to do so if you have some clue, right? So if you know that, for example, the TRR mechanism is counter-based TRR, then you want to know what will be the counter table capacity. It could be 16, it could be 32, some like random number here. So discovering that can be really easily automated. Similarly, checking if this is a per bank or like global across all banks in a chip, like this TR protection mechanism, that can also be automated. So like all these like different, let's say, columns in this table can be like automated to like gather this information. But yeah, if this is like some like mystery TR mechanism, I guess automating that is a bit more difficult because you don't know what to look at. So that's an understanding that I guess the user should build first.
I see. So the part where you slowly test for some activations and then perform some refresh operations to trigger or well, even that is speculative, right? So the first refresh operation you send does not necessarily have to trigger TRR refresh. There are a lot of parameters involved in automating all these. Yeah, I understand. Yeah. Okay.
So I'm not saying it's not possible, but yeah, it's much more difficult than just checking for the like other properties of a mechanism that you like know at a high level how it operates.
Exactly. Yeah, and my last question I think about U-TRR is maybe a bit, maybe not future looking anymore, but do you think the new RowHammer mitigation mechanisms in newer DRAM chips in DDR5, for example, there's RFM, not necessarily advertised as a RowHammer mitigation mechanism, I guess. Do you think it solves the issue completely?
Yeah. So RFM is, yeah, it stands for refresh management, and the memory controller, basically the purpose of RFM, to my understanding, is to provide the DRAM chips more time to perform these TRR-induced refresh operations, right? So I'll go a few slides back here. So here we discussed that only particular refresh commands can be used to perform RowHammer protection, right? But what if your module is very vulnerable, right? So the HC first values, the minimum activation counts are really low, and you have to basically refresh neighbors at a higher rate. So yeah, one way of enabling that is to make more of these regular refreshes to be used as TR capable refreshes, but then you may start eating from the time allocated to perform regular refresh, right? And then you may not be able to perform regular refresh at the target rate, which can be more dangerous. Yeah, so RFM is a mechanism that where the memory controller counts the activations, the number of activations to each bank, and issues an RFM command to basically provide DRAM chip more time to perform the internal RowHammer protection. But the memory controller still does not know how the TR works, and vendors also do not disclose anything about their TR implementations. So we still don't know, even with DDR5, if these chips are secure. And something like U-TRR can still be used to understand the TR mechanisms implemented in DDR5. And yeah, as you mentioned, yeah, RFM is not a replacement for TRR. It's not a RowHammer protection mechanism, but it's sort of like I would say like a side mechanism to aid RowHammer protection a little bit.
Mm-hmm. Yeah, it's giving the chip more time, as you said, to perform these TRR refreshes. Potentially, we don't know in the end what the chips do. And you mentioned that all these TRR implementations, they're proprietary and they're kept secret. I guess based on how involved this reverse engineering methodology is, I want to ask, what do you think if the manufacturers should keep this secret to, does keeping these mechanisms secret kind of prevent attackers from developing attack patterns that bypass TRR? Or ideally, should they just uncover all these mechanisms themselves? And then the trade-off, I guess, is we immediately know how to bypass the TRR mechanisms. And otherwise, we won't know until someone like you do U-TRR. But
right.
Yeah.
I mean, normally I guess you wouldn't disclose a mechanism that is supposed to be secure, but is not secure, and point out its vulnerabilities, right? I mean, you may do it in some purposes, but you should also propose workarounds, right? So I'm thinking about a particular example, but let's see. Yeah, I mean, I don't know, okay, so maybe your extreme example is refresh, right? So DRAM vendors sell modules that has to be refreshed. Okay, maybe it's a stupid example, right? But yeah, all DRAM chips are limited by that, right? So like you cannot operate it without refreshing it. So similarly, like they can implement some like partial protection for TRR and then admit that it is not completely secure. And for some corner cases, system designers should implement their own solutions. Yeah, that's possible, but maybe that's also the reason why they do not disclose this in the first place. They like maybe like couldn't put enough like logic, couldn't dedicate enough area to completely to make the TRR mechanism completely secure, and this is why they relied on security by obscurity approach. But yeah, definitely it's not working, right? So like when one person discloses that it's not secure, then it's just not secure and you cannot do anything about it. But yeah, if it is like fully secure, I guess disclosing exactly how it operates and providing a security proof, I think that would be very good.
Yeah, I agree. If they have to, if they were to disclose it, they should also, I guess, as you said, advise system designers to do something. Like for example, don't send more than this many activates per bank, which is also a difficult problem, which means you have to characterize your vulnerability to some extent. And then it becomes, I guess, a race between manufacturers because some of them have lower HC first than others. If they come up with that mechanism, that standardized mechanism, immediately some DIMMs now start to perform worse than other DIMMs from other manufacturers. Right now, they all perform the same, I guess, when you think about it, when you're operating in the standard range. But backing this partial mitigation mechanism with some sort of throttling based mechanism on the memory controller will immediately turn things around and start some competition, I guess, which could be good or bad. Bad for them, good for us.
I guess part of this discussion also is like about their business model. So
exactly.
Okay. This is what they decided to do, and they're just showing the results of our research.
Yeah, thanks. I don't see any questions on YouTube so far, and I don't have any more questions about U-TRR.
I have some. Thanks, Ataberk, for the questions. I think that discussion was actually quite insightful also. Right now, there's no difference between manufacturers in terms of latencies, right? Unless someone violates things. But yeah, once you start exposing things about RowHammer and asking the memory controller to handle it, those differences may start appearing. And it's a different kind of competition that starts at that point, right? Which is good to have, probably.
Maybe the manufacturers are not used to it.
Yeah, that certainly is true, I think. So I have a couple of questions also. So this is actually very interesting and nice work, Hasan. You have discovered a lot of access patterns. That's also very interesting. How easy or difficult are they to exploit in a, let's say, system level, full-blown RowHammer attack?
Yeah, I would say it's pretty easy. I already mentioned the biggest sort of problem, which is okay, I won't go back to that slide, but basically it's like synchronizing with the periodic refresh commands. But yeah, it's already shown by several, I guess, prior works how to do that. And you can do it, as I mentioned, in several levels at in JavaScript, in web browsers, but also in when you have total control on the system.
So you're referring to Smash and Blacksmith works? Okay.
Yes.
So basically those works that currently try to identify how to create RowHammer bit flips in a, let's say, not so well structured way, maybe more of a randomized way or fuzzing based of approaches. They can easily replace that fuzzing with the access patterns, assuming that they know the access patterns for a particular chip that would cause RowHammer bit flips.
Yeah, exactly.
Okay, that makes sense, I think. The other question I have is, can you go to slide 36?
36, yes.
Yeah, that was your goals in U-TRR. So which ones did you achieve and which ones did you not achieve so far?
Well, I would say we understand how they operate to some extent. Yeah, maybe not all the details, but we have enough understanding to develop an attack or develop access patterns for all the modules that we looked into. Yeah, we definitely assess their security. We conclude that they're not secure. Yeah, so number three, I guess we don't have like a particular mechanism that we propose instead, but there are already mechanisms that are previously proposed and proven to be secure, but this is not what is implemented in the DRAM today. It could be due to different reasons. One reason could be like, these might be costly to implement in DRAM. But yeah, there are definitely solutions to this problem. Maybe costly, but yeah, if you really want to secure your DRAM, you can do something about it even today.
Sure. Yeah, and maybe the next work is the natural next step to secure DRAM completely, right? Okay.
Good. And then we are moving to the third contribution, which is self-managing DRAM. So this is a interface and DRAM architecture for enabling autonomous and efficient in-DRAM maintenance operations. And I'll explain what these maintenance operations are. But today, memory controller manages DRAM maintenance operations, here which we identify as DRAM refresh, RowHammer protection, and memory scrubbing. So all like these three operations somehow involve the memory controller to be performed. And why is this a problem? Making changes in these maintenance operations to make them more efficient or more secure, or make them to like change them in a way to make them more reliable. Making those changes often requires reflecting the changes to the memory controller, DRAM interface, and other system components. And because of this, implementing new maintenance operations or modifying the existing ones is difficult to realize with the current way of DRAM is architected. So one very good example for this, I believe, is the new features of DDR5. I will mention the three new features they introduced in DDR5 related to the three maintenance operations that I described. So for DRAM refresh, DDR5 introduces same bank refresh, which simultaneously refreshes one bank in each bank group in a DRAM rank. So this requires a new refsp command. And implementing this new command basically requires changes in the DRAM interface and the memory controller. For RowHammer protection, we already discussed this. DDR5 introduces RFM, and here the memory controller issues a new RFM command to allow the DRAM chips more time to perform victim refresh. Again, this requires changes in the DRAM interface and memory controller as a new RFM command is introduced, and also the memory controller has to keep track of activations happening in each bank. And third, memory scrubbing. For memory scrubbing, DDR5 uses on-die ECC, which is now in the standard, and as opposed to DDR4, every DDR5 DRAM chip has to implement on-die ECC according to the specification. They use this on-die ECC also to perform periodic scrubbing, also called patchwork scrubbing. And although this does not necessarily require changes in the DRAM interface, it can be, it doesn't require changes when it is configured to perform scrubbing when DRAM is in self-refresh mode. But there's also like another mode where the memory controller issues a scrub commands to initiate those scrubbing operations manually. So we conclude that DDR5 changes are difficult to implement as they were only possible after multiple years required to develop a new DRAM standard. So here I should emphasize that developing a new DRAM standard does not take long necessarily because of it's difficult to implement these operations, but it just takes time to develop a new DRAM standard that involves many other things, mainly making the I/O much faster and then solving other scaling issues in the architecture of the DRAM. We propose self-managing DRAM, or SMD for short. The key idea of SMD is to prevent the memory controller from accessing DRAM regions that are under maintenance by rejecting row activation commands. So here, basically, the ability to activate row activation, the ability to reject row activation commands is the way we enable autonomous in-DRAM maintenance operations. And to provide the DRAM chip with this ability, we add a single additional pin to each DRAM chip. And this is a pin that is used to provide a negative acknowledgement, or ACK-NAC, to the memory controller. And I will explain how that operates in the next slide. But basically, leveraging the ability to reject and activate command, a maintenance operation can be implemented completely within a DRAM chip without any other changes in the DRAM interface or in the memory controller. Right, so using this approach, you can implement refresh, you can implement memory scoping, you can implement RowHammer protection. And memory controller does not have to do anything about it, or we don't need to make any additional changes in the DRAM interface. Here's a simple example of how the simple illustration that shows how the DRAM bank architecture looks like in SMD. We logically divide a bank into multiple regions. The reason we do that is to prevent putting the entire bank under maintenance, where the entire bank will be unavailable until the maintenance finishes. So we logically partition a bank into multiple regions so that we can lock a single region for maintenance and for accesses to only one region, while the memory controller can keep accessing other regions in the same bank. So these lock regions are configurable in size, and vendors can decide what their lock region size should be according to like their DRAM design. Here, for each bank, SMD also implements what we call lock region table. And this is basically a table that has one bit for each lock region here, indicating whether the region is under maintenance or not. So the SMD controller uses this table to decide if an incoming activation command should be rejected or not. And SMD rejects any activate command that targets locked region by sending the memory controller an ACK signal. This is what I already mentioned. Yeah, so here's like a quick illustration. So let's assume the memory controller issues an activate that targets a row in bank 0, lock region 0. And at this point, the lock region table has this status over here, where the lock region 0 is locked and other regions are available. So because the target lock region is locked, the DRAM chip will send the ACK signal, and the memory controller receives the signal after T cycles. This depends on the design of the DRAM chip, but we don't expect this to be too large to delay the operation of the other commands. So after receiving this negative acknowledgement signal, the memory controller should retry the same activate command to service the pending request. And the memory controller does that after a fixed interval, here that we call act retry interval. And after the retry interval, the memory controller issues the same command. And in this example, the lock region 0 is available at this time, and the activate command will go through and the row will be opened. And for this second time, for the second activate, the memory controller does not receive an ACK signal. In the meantime, while waiting to retry the previous activate command, the memory controller can issue activations to other rows in different lock regions in the same bank or to different banks, as it can do that today. Okay, using SMD or self-managing DRAM, we develop various maintenance mechanisms. For DRAM refresh, we develop fixed rate refresh, which uniformly refreshes all DRAM rows with a fixed refresh period. This is exactly how DRAM refresh works today. So we just integrated that into included that in the DRAM chip, and in this fixed rate refresh, the memory controller does not have to issue refresh commands periodically. So like we take that responsibility from the memory controller. We propose a second maintenance mechanism for DRAM refresh, which we call variable refresh, or smd-DRR. This mechanism uses retention profiling information to skip refreshing rows that can retain their data for longer than the default refresh periods. So basically, this mechanism requires profiling information, and if a row is profiled to have like very high retention time, then yeah, it can be refreshed at a much lower rate than the default refresh rate. For RowHammer protection, we also propose, we proposed 3 mechanisms actually in the paper, but here I will mention 2 of them. We propose probabilistic RowHammer protection, which is similar to the para mechanism proposed in the first RowHammer paper in 2014. With each activation command, there is a small probability to refresh the neighbors of the activated row. And this is how this mechanism works. So this is similar to like that sampling-based approach that I described in the U-TRR work for vendor B. But here the difference is that, so there, because of how TRR works and the TRR-induced refreshes can only happen at certain refresh commands, that limits basically the total number of neighbor refreshes that can be performed. But here you don't have that limitation, right? So if you properly tune the probability to perform neighbor or refresh, this mechanism can be statistically secure. Second, we proposed smd-DRP. This is a deterministic RowHammer protection mechanism, which keeps track of most frequently activated rows and performs neighbor or refresh when the activation count threshold is exceeded. So this mechanism is similar to graphene, the work that I mentioned, which was published in 2020. It like basically uses a counter table to keep track of n most frequently activated rows. Again, if you configure this table properly, if you have enough counters, enough entries in this table, this can be deterministically secure mechanism. And last, we developed mechanism for memory scrubbing. smd-MS periodically scans the entire DRAM for errors and corrects them. So this is similar to how fixed refresh work, but performing scrubbing is a bit more complicated task than refreshing, because refreshing can be simply done by activating a precharging row internally in the subarray. Here, to perform periodic scrubbing, we need to like fetch the data, send it to the ECC engine, run the ECC decoding to like see if there are like any bit flips in the code word, and correct them and write them back if correction is necessary. So thanks to SMD, all these mechanisms can be implemented completely within DRAM, and they can also operate together. And in particular, I guess we selected SMD-VR, SMD-DRP, and SMD-MS as the like 3 main mechanisms that we use in our SMD combined mechanism that we will later see in the results. So before showing the evaluation results, I will briefly mention the methodology. We evaluate the performance and energy efficiency benefits of SMD using RemulaTor and DRAM power. We simulate 44 single-core workloads and 64-core multi-program workloads, which we crafted by randomly choosing from the single-core workloads. We simulate the system with these parameters. It's a 4-channel dual-line DDR4 DRAM that we simulate with 32 millisecond default refresh period. Okay, and in this slide, I will show the single-core speedup for the 5 maintenance mechanisms that we implemented. Plus for the SMD combined mechanism that I mentioned, and also an ideal mechanism that we implement. So here I would like to mention that for the RowHammer protection mechanisms and for the memory scrubbing, we use smd-FR as the refresh mechanism. Right, so like, I mean, obviously DRAM cannot operate correctly without a refresh mechanism. So in this, for like individually evaluating the benefits or the overheads of the RowHammer protection and memory scrubbing, we use the simplest refresh mechanism that we have here, which is the fixed rate refresh. Yeah, as I mentioned, we also evaluate SMD combined, which uses smd-DR variable refresh, rate refresh determines RowHammer protection and memory scrubbing in combination. We also show here an ideal mechanism named no refresh. This is a DRAM, idealized DRAM that does not perform, that does not require any refresh, and RowHammer protection and memory scrubbing. So we just assume that it can operate reliably, correctly, in a secure way without any refresh and any sort of protection. So this is really the upper bound of the performance benefits we can achieve by making the maintenance operation efficient. And the observation we make here is that with SMD combined, we can achieve performance benefits very close to the benefits that we achieve with this ideal mechanism. And for the other individual mechanisms, we can see that SMD-FR and SMD-DR improve the performance by a significant fraction on top of regular refresh. And this is mainly because we enable accessing different banks and different lock regions inside the bank when a maintenance operation is happening. In DDR5, there's only rank level refresh, and when a refresh is happening, basically the entire DRAM rank cannot be accessed. And yeah, the main benefits in the fixed refresh rate comes from that. In a variable refresh rate, there are additional benefits due to not refreshing rows that can retain data for longer than the default refresh period. And other RowHammer protection mechanisms and memory scrubbing benefits still outperform the DDR4 baseline. So here all the speed up results are in comparison to DDR4 baseline. So these still provide benefits because we use the fixed refresh rate as a refresh mechanism. So the way to look at the overheads of RowHammer protection memory scrubbing is to look at how lower speed up, how lower these bars are from the fixed rate refresh mechanism.
Hassan, I have a question. Maybe you described it and I missed it. But for SMD combined, you say we have 9.2% speed ups. And for variable refresh alone, it looks as if the speed up is higher. Is that correct? And
yeah, it's correct.
Okay.
So for SMD-DR, we don't do RowHammer protection memory scrubbing, right?
I see. Okay, yeah, that makes sense now. Okay, I missed it. Yeah.
So the difference is basically the overhead of these two mechanisms that we have here. Okay, and so I won't talk about this in detail, but we because of these speed up benefits, we also get a reduction in DRAM energy. So this plot shows the normalized DRAM energy, again, normalized to conventional DDR4 DRAM. And yeah, we see that the DRAM is consuming a lot less energy. And this is close to the ideal mechanism here, again, without any refresh and protection. So similar to...
I have a question, Hassan. These are very good results. What RowHammer threshold are you assuming?
Yeah, it's pretty low actually. Here we assume 1K.
Okay.
So it's like 1,000 activations.
Okay, and these are, yeah, go ahead.
So that lowering the activation threshold does not translate to too much performance overhead, but with deterministic RowHammer protection, at least, that requires very large counters, like a very large number of counters. So here for this at 32 millisecond refresh, we need about close to 1,000 counters, which may be quite costly to implement in a DRAM chip.
And you assume that those counters are there,
right?
For the deterministic RowHammer protection mechanism.
Yes.
Okay. Yeah, go ahead.
I was just going to say that 1K activation count is a bit extreme to consider. Sure, you may see those values in future DRAM chips, but today, even the lowest HC values, as we show in the table, in the order of 6K to 7K.
Yeah, but we're almost there.
yeah, we are almost there. Yeah.
The other question I think you already answered is you're assuming 32 milliseconds. refresh interval rate. Okay.
As a default refresh rate. Yes.
For all of these. Okay.
Yeah.
Okay.
So these are also the 4-core results. We have very similar benefits due to like the same reasons. The only difference here that 4-core experiments make is that like in 4-core experiments evaluations, we have multiple workloads that run simultaneously on the same system. So they cause more stress on the memory subsystem. So like the memory intensity is much higher. But as we see, that does not necessarily cause a problem, and we get similar speedups. It does not like help significantly as well. Like in general, I guess like here, as we reduce the overhead of refresh operations, the memory intensive applications would benefit more from that. So that's for sure. But like the difference between single core and 4-core is not huge. Maybe mainly because here we don't, these are average results for the single core workloads, but we only included workloads that have some level of memory intensity. So we excluded those that do not access memory too much because like those are not relevant, right? So, and yeah, so like when we like consider these like memory intensive workloads, we see similar benefits for both 4-core and single core. And yeah, the conclusion is that SMD-based maintenance mechanisms have significant performance and energy benefits. But I would like to mention that the biggest benefit, in my opinion, of using SMD is that vendors can freely change the maintenance mechanisms they implement in their DRAM chips without waiting for the next DRAM standard for the next generation to be published. And yeah, they can just innovate at a much higher, faster rate. One last plot that I would like to share is this plot that shows the sensitivity to the refresh period. So here we showed how SMD-FR and SMD-VR, the two refresh mechanisms, and SMD combined perform, or like we show their speedups normalized to DDR4 baseline, and also the no refresh mechanism for different refresh periods for 64, 32, 16, and 8 milliseconds. And here we can clearly see that as we reduce the refresh period, which might be necessary in future DRAM chips that are more leaky and necessitate refreshing at higher rate to operate reliably. Here we see that the average speedups improve, like are in like about 20% for 16 millisecond and 50% for 8 millisecond refresh. So this shows that the current approach to refresh, like that all rank refresh in DDR4, also does not scale well in terms of like performance, in terms of like efficiency, as the refresh period reduces. And we conclude that SMD-based refresh mechanisms will be even more beneficial in future DRAM chips with low refresh periods. So as for the hardware overhead, enabling SMD on top of conventional DDR on top of conventional DRAM chip requires small changes. It's well, maybe not necessarily small, but I would say relatively small. We need to add a single pin per DRAM chip. This may not be necessary depending on the constraints a DRAM vendor has. So like there are like other options. A DRAM vendor might be able to reuse existing signals. So for example, there is a signal called alert N that is used to alert stuff like a failure in CRC checks and like exceedance on temperature. So like the usage of that signal, I guess, is not like specific. It can also be used for other purposes depending on how the manufacturers extend that. But anyway, so regardless, so if like there is like a big hesitation to add a new signal, the new SMD standard can also be like designed in a way to repurpose existing pins, such as the alert pin that I mentioned. Second, inside the DRAM chip, SMD implements a lock region table that we discussed, which incurs only about 32 micrometers squared area overhead, which is a very, very small percentage of a typical DRAM chip. Yeah, this overhead is very small because we need to store only one bit per region. And yeah, so like even having like 8 regions per bank is pretty useful to hide the latency of the maintenance operations. Yeah, and also because of like being very small, the access latency of this table is also very small, so it doesn't like cause additional delay. On the memory controller side, we also made some changes. These changes involve by handling the new connect signal. So when the activation is rejected, the memory controller needs to make changes to handle that, to retry the same activation command in the future. But besides these changes, we also simplified the memory controller a little bit. So the memory controller no longer needs to manage DRAM maintenance, right? So it doesn't have to issue the periodic refresh operations. It still has to implement DRAM timing parameters for accessing, but it doesn't have to implement other timing parameters for refresh or for memory scrubbing or RowHammer protection, right? So like RFM might not be required, might not be needed because the DRAM chip with SMD can enter maintenance to perform RowHammer protection at any time. In the paper, we have other results. We have lock region size sensitivity. So we see how the speed up benefits change as we put fewer or more lock regions per bank. We compare SMD-based RowHammer protection against conventional memory controller-based RowHammer protection. By here, memory controller-based, I mean like stuff like performing para at memory controller level. We also compare memory controller-based scrubbing against SMD-based scrubbing. We sweep the activation threshold, like the minimum activation counts to use when protecting against RowHammer for the deterministic RowHammer protection mechanism. So this is important as this changes the number of counters required to provide the security. And finally, we also look at the sensitivity to victim row window. So this is like the window of victim rows that hammering a particular aggressive row can affect, right? So like so far, I guess we've seen that only the 2 victim rows can experience bit flips due to hammering the row between them. But like going to like denser DRAM designs, RowHammer can also cause bit flips in other rows as well, right? Like 2 rows away or 3 rows, 4 rows away from the aggressor row. And we looked into that basically. If that changed, and if you need to refresh more rows at once instead of just 2 rows, how that translates to system level overhead.
Hassan, I have some questions maybe before you summarize. The first thing is, you talked about the alternative implementation for the additional pins.
Okay.
But did you actually measure the overhead in any way for adding a new pin? Do you have numbers on that in the paper?
Yeah, so no, we don't have numbers actually. So that's a bit difficult because like the floor plan like will also depend on the rest of the design. So like I'm not sure if that will be like accurate to do without like having the like, proper at least like higher level design of the DRAM chip. But yeah, I mean I guess one can make a very rough estimation based on like let's say comparing DDR3 and DDR4 or DDR4 and DDR5. I would assume like the pin count increase in DDR4 and then just like roughly like seeing how much like the chips increase.
Yeah, I guess you could you're talking about comparing like actual chip sizes if there's like a difference between generation to generation.
Yeah, so I guess that won't be very accurate because like the die size might not be good indication of like, well, there might not be like very good correlation between the package size, package dimensions and die size. But yeah, still, I guess we'll give an idea. I don't know, like,
yeah,
we did an analysis.
And in the worst case, well, not worst case, but there are alternatives, as you mentioned, like existing pins can be utilized for this. We have a comment in the chat from Ozargin also, asking how you measured the overheads, possibly referring to the area and the performance results.
Okay, so for the performance and energy used to emulator and DRAM power, so we basically modeled our changes there. So we implemented this lock region table and like all the SMD operation, like the ability for the memory controller to reject activation commands. So like we modeled all that in the emulator, and also incorporated those changes to DRAM power. Well, we did not do any changes in the DRAM power actually, except that to like sort of overestimate the energy overheads, because like it was difficult for us to properly model how much energy rejected activations will consume. We basically assume that even if an activation is rejected, it will consume as much energy as regular activation that is not rejected. So this was the only change we made in DRAM power. And for the area overhead, for the lock region table, we modeled that in Cacti. So Cacti 3DD has a simple model for a DRAM chip. So we like modified that to include our changes here.
I see. Yeah, it makes sense. I guess that's kind of best effort in this age of DRAM overhead estimation.
Maybe not, but this was like the best to our knowledge.
I have a follow-up question on the, well, not necessarily a follow-up, but we have this new ACT-NACT pin. Can we, as far as maybe you're already aware, but there are a way to mitigate RowHammer is to throttle memory controller requests. And basically, if the memory controller itself counts the activations per bank, per row, and make sure not to send basically more activates than what it should to guarantee that no bit flips occur. Could this ACT-NACT pin be used by the chip to implement such a throttling mechanism? So for example, in this way, basically the chip counts activations to all rows. I guess the advantage is the manufacturer gets to keep the tracking mechanism to itself, doesn't expose it, and tells the memory controller that that activate you sent was ignored by me because you exceeded the activation count.
Yeah. So yeah, it's certainly possible. But yeah, I'm thinking, why would you want to do that instead of refreshing the victims? So like refreshing the victims might be more efficient in terms of like the time required to perform that refresh. But throttling access, especially at low activation rates, would take a very long time, right? So you basically need to throttle accesses to the entire region.
True.
Or if you keep track of that at region level, if you keep track of that at row level, we can do that and to the row level. But basically, you may delay that access for a very long time until the row is refreshed by the refresh mechanism. Yeah. So BlockHammer, the idea in BlockHammer, I think, is much better because it is like it differentiates benign and malicious applications, right? So throttling accesses of malicious applications I think is a more logical thing to do compared to throttling everything.
Yeah, especially if you do it. Yeah, go on, please.
Yeah, I was just going to say, throttling everything can become very, very expensive at low HC first, low activation counts.
I guess if you're keeping, I was gonna say if you're keeping track of the activations in lock region granularity, and that's larger than a row, potentially you're introducing another denial of service attack vector by allowing attackers to, exceed the counters of a lock region where a benign application is accessing, and the benign application now cannot access it. Yeah, I guess it's not really a good idea to do it directly, as I guess without thinking about it at least. Okay. Yeah, that was my question.
Well, Hassan, I have some comments and question. So I think this is actually a nice step in the right direction, in my opinion, in terms of rethinking the DRAM interface. It doesn't completely change it, but it adds some flexibility to it so that the DRAM chip performs some internal operations without, let's say, disrupting the interface too much. So I like that from that aspect. It breaks this inflexibility or the too much synchrony, let's say, between the DRAM and memory controller, right? So you add some asynchrony that enables that sort of flexibility. So that's good, I think. The question I have, one question I have is related to memory controller modifications, the slide basically. Yes, you do need changes to request scheduling, no question about that, but this adds some unpredictability also to the memory controller. The question is how bad is that unpredictability? Like how long is the memory controller going to wait? What policies is it going to adopt to retry the activate? Do you have any thoughts on that? Because this depends on the maintenance mechanism and its latencies as well, right?
Yeah, exactly. So it's entirely maintenance operation dependent. So the way we designed it, for example, we designed the refresh mechanisms to like refresh a few rows at a time. So once a maintenance operation happens, let's say we lock a particular region, the refresh mechanism refreshes 8 rows from that region and then unlocks the region. And the next time it switches to another lock region. The reason we do that interleaved way of refreshing rows in different lock regions is to not to keep busy the same lock region over and over. So like if like these maintenance operations are designed carefully in this way, and they are designed in a way that they do not cause a deadlock, right? So like they do not continuously keep a region locked. I think the predictability, the divergence in response times can be still predictable. Well, maybe like in case of variable refresh and RowHammer protection, maybe that could add some unpredictability because variable refreshes depends on the profiling information, and RowHammer protection depends on the access pattern of the application. But still, like a single region should ideally not remain locked for a very long time.
So I think you're saying that you can bound the unpredictability by bounding the maximum amount of time a region can be locked. Yeah, that makes sense, I think.
That could even be like imposed as a requirement to like in the specification, right? So let's say, so the specification doesn't like dictate any particular refresh operation, but it may say, okay, with SMD, you should not have a region locked for more than this. And manufacturers will need to make sure that their maintenance mechanisms comply with that.
Yeah, I think that makes sense actually. That eases the memory controller design, especially in handling quality of service, right? Or quality of service critical requests. Okay, I think I have one more question on. So these ACT-NACT signals happen at the chip level, right? But the memory controller operates at the rank level. Let's say, how do you handle that discrepancy?
Yeah, so actually we also looked into that in the paper. We call it ACT-NACT divergence across DRAM chips. So there's a chance that Since DRAM or maintenance mechanisms in DRAM chips operate independently from each other, one DRAM chip may lock a region while others do not. And as a result, when you try to access row in that lock region, some chips may reject the activation, but some may not. And that will result in partially activating the row in some rows, in some chips, but not in others. So there are multiple ways to deal with this. One is to just observe that the activation went through partially and retry activating other chips that rejected the activate command. So yeah, this is one solution. And once you issue an activate that does not produce any rejects, then the memory controller makes sure that the row is fully active. Another approach is to, upon like seeing a divergence, pre-charging the row, and then retrying activating the whole row at once at a later point. Yeah, we implemented and analyzed both of these three approaches and also a hybrid approach, sort of in between. Yeah, so but I would also like to mention that this applies to only this particular design that is using these like module-based systems, right, in DRAM that we so far discussed. But there are also other types of DRAM, such as like HBM and like LPDDR, GDDR that does not necessarily like have this rank level organization composed of multiple chips. Mm-hmm. So for those, this problem does not apply. But even for DDR4, like these module-based systems, it's also possible to move this SMD logic to the buffer chip, which is also called register. So like there are register DIMMs that employ an additional chip on the module to buffer the incoming request and also like the data to like reduce the load, the electrical load on the channel, such that it allows like plugging in more modules and like inserting more ranks into the system, basically. So yeah, if you implement this in the register chip, if you implement the SMD register chip, it may also help to reduce the number of activation signals that go to the memory controller.
Yeah, I mean, that makes sense, I think. But it will still need to be done at the register, like the buffer.
Yeah.
I agree. I think it doesn't apply to, this problem doesn't exist in all DRAM standards, but it does exist in some of the important ones like DDR4, DDR5. And so I'm curious which approach was the best among the ones that you described, pre-charging, waiting, or the hybrid.
Yeah, so the difference wasn't huge in the workloads that we analyzed. So it was like very small. Pre-charging was better overall, especially like when we factored in energy. Because like when a row is partially open, it consumes more energy than the other chips that did not reject the activate command. Sure, it also consumes some energy to pre-charge the row, but I guess it's a function between like how long it takes for the memory controller to retry a rejected activation, which is determined by how long a maintenance operation takes. So in our evaluations, pre-charging was slightly better, but yeah, depending on what is the maintenance time, typical maintenance time, I should say, that may change. So waiting might be more beneficial.
Yeah, that makes sense. And all of these results are in the archive paper, right?
Yeah.
Okay, thanks.
Very good. Then, yeah, I guess I didn't cover this slide where I summarized the self-managing DRAM. There are three major DRAM maintenance operations for refresh, RowHammer protection, and memory scrubbing. We observed that implementing new maintenance operations is difficult to realize. And our goal was to ease the process of enabling new maintenance, DRAM maintenance operations and also enable more efficient in-DRAM maintenance operations. And to this end, we propose Softmc DRAM, which enables new in-DRAM maintenance operation mechanisms with no further changes in the DRAM interface and the memory controller. We also show that SMD-based refresh RowHammer connection and scrubbing achieve 9.2% speed up and 6.2% lower DRAM energy compared to conventional DDR4 DRAM. The source code will be available soon on GitHub and can be accessed with this link. It's not like fully ready. We didn't release it yet, but I guess, do we give a specific time here? I guess we don't have to, but yeah, it will be released very soon in a week or two. Okay, now I will discuss the last and fourth contribution, which is copy row DRAM or CROW. CROW is a low-cost substrate for improving DRAM performance, energy, efficiency, and reliability by making a simple change in DRAM that enables new operations. But briefly, I will just again remind you the DRAM scaling challenges. There's basically a trade-off between data integrity and latency. It's possible to reduce the latency of DRAM, but you probably give away some DRAM capacity or data integrity. You make your DRAM less reliable to provide a higher latency DRAM or lower latency DRAM, sorry. But anyway, so these scaling problems translate to system level problems such as performance, energy efficiency, reliability, and security with approximation. We observed that the underlying density optimized DRAM cell array structure may incur non-negligible area overhead. So making any changes in this density optimized DRAM cell array for the purposes of improving DRAM latency is not that easy and results in very high overhead. Our goal is to lower the DRAM access latency, reduce refresh overhead, and improve DRAM reliability with no changes to the DRAM cell structure and only minimal changes to the DRAM chip. And we do that with a flexible substrate that enables new mechanisms for improving DRAM performance, energy efficiency, reliability, and security. The key idea of this new substrate is to efficiently duplicate select rows in DRAM and exploit duplicated rows in new mechanisms that provide low latency access and more efficient refresh. So here's a high-level overview of the substrate. This is a conventional DRAM subarray that has a row decoder, a bunch of DRAM cells organized in two-dimensional array, and sense amplifiers. We modified this slightly by partitioning this DRAM subarray into two. So they're regular rows. These are just similar to conventional rows. And we also have some rows that we designate as copy rows. These are also like just conventional cells in terms of like the cell architecture. But what is different is that they're controlled by a separate row decoder that we call CROW decoder. And this enables independently activating one regular row and one copy row at different times. So using this design, we enable two operations, a row copy operation, which efficiently duplicates data from a regular row to a copy row, or it can also be done vice versa. And the second operation enables two-row activations, where this results in quick access to a duplicated row. So basically, if a regular row and a copy row contain the exact same data, you can activate both at the same time. And that results in lower latency access due to reasons I will explain next. One more component that CROW has in the memory controller is the CROW table that basically keeps track of the mappings, right? So like which copy row is duplicate of which regular row in each subarray. So the purpose of this CROW table is basically to keep track of all these mappings. Okay, so let's go over the row copy operation first. So at the system level, we implement a new command to support this. The memory controller issues a actc command. This is a sort of a different version of the activate. So what this command performs is it first activates a regular row. And after the data of this regular row is loaded into the sense amplifiers, without closing the row, CROW activates a second row, one of the copy rows. And this results in the sense amplifier driving the same data to both of the upper rows. Effectively, we create a copy of the regular row that we first activated. And here's an illustration explaining how this works. So here we explain that with a single cell in a source row and destination row, Here, our goal is to copy the content, here the like fully charged state from the source row to the destination row. The first operation is to activation of the source row, which basically connects the cell to the bit line. And after charge sharing happens and the sense amplifier gets enabled, the restoration starts. And at this point, we also enable the access transistor of the destination row. And this results in sense amplifier restoring the charge to both of the source and the destination row at the same time. Okay, and this is basically how the row copy operation works quickly, and we copy one row from one row to another row within the same subarray. Yeah. And the second operation is the simultaneous activation of two identical rows. And this is very similar to the previous operation. The memory controller initiates this with a separate command called act-t, and stands for two-row activation. The only difference from like the previous operation is that instead of activating rows one after another, these two rows activated at the same time. So here the memory controller knows which rows contain the same data. They are like copies of each other by looking at the crow table that we discussed in the previous slide. Yeah, and activating these two rows at the same time results in low latency access. And let me explain why. So here again, we have two rows in two cells in two different rows. And we know that both of these cells are both discharged or charged. And here in this example, we assume both of them are charged. After the simultaneous activation of these two rows, they together share their charge with the sense amplifiers. Here, effectively, we create a single cell that is larger, 2 times the size of a single cell. And this results in fast operation as it drives the sense amplifier faster to the target voltage level or charge level. And later activating the sense amplifier and the restoration step can be performed also much faster compared to normal operation. And this enables fast access to data that is duplicated across a regular row and a copy row. Based on these two operations, we designed 3 mechanisms called crow cache, crow ref, and a mechanism for mitigating RowHammer. Let's first discuss crow cache. The problem that this mechanism tries to solve is the high access latency of DRAM. The idea is to use copy rows to enable low latency access to recently activated regular rows in each subarray. So essentially, we are creating a cache region in each subarray by taking advantage of the 2 operations that Crow provides. So Crow cache uses row copy to copy a newly activated regular row into a copy row. So this newly activated row is basically recent access row that we expect to be activated in near future again. And this is why we create a copy of it. And next time the same row is about to be activated again, instead of issuing a normal activate command, the memory controller issues the two-row activation command to activate the regular row and its copy at the same time. Choose some spike simulations, we observe that this operation reduces activation latency by 38%. And here's the slide that shows the example operation of crow cache. So let's assume you have a clean crow table initially. And here's the request queue that will contain the accesses to be performed. We assume initially we get a load request to row X. So this is a crow table miss since the crow table is initially empty. This crow table miss initiates a row copy operation. So a copy row is being allocated as a first step, and the memory controller issues act-c. So there is like no need to issue a separate command to perform this load operation, right? So the memory controller, instead of issuing the normal activate command, can just issue act-c to activate the regular row with by also copying it. So this copy operation does not prevent the row from being accessed because the data is loaded to the sense amplifiers. Okay, and this is how we create a copy of this row that was accessed, and it got a miss on the crow table. And then let's assume we got a bank of it, right? So the memory controller had to close this row that was open with the actc command, and the memory controller just activated another row, and let's assume that's a row in another subarray, not in this subarray. So then, yeah, once again the memory controller receives a request to row X, this is possible because even in case of a cache, because we might be accessing with the second load a different region in the same row. A typical DRAM row is about 8 kilobytes in size. So yeah, so it's possible that not this entire row is accessed at once, but it is accessed at different times. Different regions of the row are accessed at different times. Okay, the second row this time will be a crow table hit, and this means that the memory controller can issue 2 row activations and perform low latency access. Yeah, and here, because the second activation of row X is faster, overall we get latency reduction benefits by using crow cache. Okay, moving on to the second mechanism, which CrowRef uses a mechanism for reducing the overhead of refresh operations. Yeah, so this mechanism deals with the high overhead of the refresh operations. One observation we exploit here is that there are weak rows and strong rows in DRAM, right? So like it's very like few rows, in fact, in DRAM must be accessed, must be refreshed at a high rate, at the default rate, 64 milliseconds, for example. And here we define a weak row as a row that has at least one cell that cannot retain data correctly when the refresh rate is decreased or the refresh period is increased. And the key idea is to safely reduce the refresh rate by remapping a weak row to a strong copy row. So here, basically, we enable a mechanism that can be that can perform this remapping, both at design time, boot time, or even at runtime, right? So there can be like a mechanism that continuously profiles the errors in DRAM, and once like there's a row detected that has like retention failures, that row can be remapped. So this runtime mechanism can maybe useful, especially if the system is equipped with ECC, right? Because otherwise the flips may just corrupt data and crash the system or cause some like other issues. Yeah, so by remapping these weak regular rows to strong copy rows, CrowRef eliminates more than half of the refresh requests. Here's an example that illustrates how CrowRef operates. So we first perform retention and profiling. Right? So this mechanism requires this knowledge in advance, knowing which regular and copy rows are strong, which are weak, meaning which can correctly retain data if we like half the refresh rate, for example. The second operation after profiling is to remap weak regular rows to strong copy rows. And on activate, instead of accessing the weak copy rows, the remapped copy rows, the remapped regular rows, the memory controller will activate the copy row that the weak regular row was remapped to. Okay, so like it's pretty simple, just remapping based mechanism that requires some retention time profiling information in advance. But the efficiency or effectiveness of this mechanism is based on how many weak rows exist in DRAM chips. If the majority of the rows are weak, this mechanism will be very difficult to use and it will provide very little benefit. It turns out that weak cells are very rare, and consequently, weak rows are also rare. So there's a prior work from 2013. There are also other prior works more recent than this one that analyze the retention time of the DRAM cells, but at the time of this publication, this was the work that we referred to for this information. So this work shows that there are very few, only about 1,000 cells that cannot correctly retain their data when the refresh period is increased to 256 milliseconds. And this is across a 32 gigabyte DRAM module. So yeah, the number of total cells are very, very, very small. So based on this information, we calculated the probability of number of weak rows that can be located inside a single subarray. So these probabilities tell us how many copy rows will be needed on average when we do this remapping. So yeah, with this data, it is very likely that there will be at least one weak row in each subarray, assuming the subarray sizes in our configuration, which is a subarray with 512 rows, if I remember correctly. But the probability of having 2 weak rows or 4 weak rows, 8 weak rows is very, very small. So this basically means even with 4 copy rows, we will be able to remap all of the weak regular rows with very, very high probability. And even if we cannot remap, that's not a problem because we can just design a mechanism that will fall back to refreshing that entire subarray with a default refresh rate. But still here, the probabilities are very small and suggest that even a few copy rows will be sufficient to remap all the weak rows. Yeah, so to profile the rotation time of these weak rows, we just here say that one can use prior works that propose approaches or ways mechanisms to profile the retention time of DRAM modules. Yeah, and this profiling can be done at both boot time or during runtime. We conclude that even a few copy rows are sufficient to halve the refresh rate or like to remap the weak rows. So depending on like how you tune your how you decide a row to be weak, right? You may extend the refresh rate even more aggressively. But in this work, we assume that for weak rows, we keep refreshing them at 64 milliseconds. But for strong rows, we increase the refresh period to 128 milliseconds. Okay, and last, I will briefly explain the mechanism we developed for mitigating RowHammer. We didn't develop here a very detailed mechanism, but we just highlighted some its key operation, but we didn't evaluate it in detail as we did for the other 2 mechanisms. Yeah, so we already discussed RowHammer, so it just happens by rapidly activating and charging an aggressor row. Here, the key idea of this mechanism is to, when an aggressor row is detected, so we leave the detection of the aggressor row to like another work, right? So like there has to be a mechanism that will detect an aggressor row. But upon detecting an aggressor row, one approach is to move the victim rows to copy rows. So this may sound a bit unnecessary at the beginning because like to move these victim rows to copy rows, we have to activate them. And activating the victim rows replenishes the charge of these victim rows, like refreshing them, which is also mitigating RowHammer. But what can be useful about this mechanism is that once moved, like once these victim rows are remapped to copy rows, attacker can keep activating, like keep hammering this aggressor row, right? And for these like future activations, you don't need to take any other action, right? So these 2 rows are secure, they are protected. Yeah, and so this is basically the key idea that we propose here for RowHammer protection. So our evaluation methodology is very similar to how we evaluate Softmc DRAM. We use DRAM emulator for performance simulation. We use DRAM power for DRAM energy evaluations. Here we again evaluate for the 4 single core workloads. We craft 160 multi-program 4-core workloads with various memory intensities. And we execute at least 200 million representative instructions per core for these workloads. We use a 1 and 4-core system with 8 megabyte LLC. We assume LPDDR4 memory in this case in our default configuration, and we assume 8 copy rows per subarray with 512 rows, 512 regular rows. Okay, so let's start with looking at the performance and energy benefits of Crow cache. This figure shows the average speedup that Crow cache provides for single core and 4-core workloads. For both, Crow cache provides 7%, about 7% speedup, which is very close to an ideal hypothetical mechanism where a Crow cache has 100% heat rate. So Crow cache also saves significant DRAM energy, mainly because of reduction in execution time. So Crow cache improves single core and 4-core performance and energy. So if you look at the Crow graph results, so similarly, we get speed up benefits. This is because we eliminate many of the refresh operations, and the time normally allocated for refresh operations can be used to perform accesses. We also have so these results are for 8 copy rows and 64 gigabit DRAM chip, but we have a sensitivity in the paper to like the number of copy rows and also the sensitivity to the DRAM chip. Yeah, and both for single core and 4-core systems, again, with Crow cache, we get significant speed up and DRAM energy benefits. So we show that these two mechanisms can be also used in combination, because like after remapping the weak rows, usually there are not too many weak rows per aggressor rows, too many weak rows per subarray because of the probability plot that I showed previously. So after doing that remapping, there are still a lot of copy rows that can be used by Crow cache for as a like caching space. And combining these two mechanisms basically improves the speed up and energy benefits even more, as these two mechanisms can work synergistically. And here we have a comparison to ideal Crow cache and no refresh. So here, this is again, hypothetical mechanism that always accesses all rows with low latency, the same latency that we use to access in the case of a Crow cache hit. And at the same time, this ideal mechanism does not perform any DRAM refresh. So this is an upper bound of improvement and DRAM of performance improvement and DRAM energy reductions we can get out of these mechanisms. Okay, so we conclude that in combination of Crow cache and Crow provides more performance and DRAM energy benefits compared to using each of the mechanisms alone. So we again model the hardware overhead of a Crow, and with 8 copy rows and 16 gigabyte DRAM module, we show that the Crow incurs about 0.5% DRAM chip area overhead and uses about 1.6% of the DRAM capacity. And at the memory controller, for the Crow table, the Crow table requires about 11 kilobyte of storage area. So we conclude that Crow is a local substrate, and please refer to the paper for more detailed hardware overhead evaluation. We also have other sensitivity studies and results in the paper. So we look at how the performance and energy benefits change when we use different number of copy rows per subarray, when we change the DRAM chip density, we change the loss level cache capacity. We also show Crow cache results with prefetching enabled, and also we compare Crow cache to other in-DRAM caching mechanisms, TLDRAM and SOLP specifically. So we have the source code available on GitHub for Crow. There we have the source code for the SPI simulations that we use to show how we get the latency reduction when we simultaneously activate 2 rows at the same time. And also the source code for RAMulator, for the modified version of RAMulator that includes the Crow mechanisms. So in a summary, copy row DRAM is a local subset that introduces copy rows into each subarray, where these copy rows enable efficiently duplicating data from a regular row to a copy row. And these duplicated rows can be quickly accessed to improve DRAM latency. We also show that remapping a regular row to a copy row can also be used to improve to reduce the refresh overhead and also enable RowHammer protection. Yeah, and we developed 3 use cases, and we evaluate 2 of them mainly, crow cache and crow ref. But we also mention how RowHammer mitigation mechanisms can be designed using crow. Yeah, going forward, we hope crow enables many other use cases. And yeah, this was yeah, the end of the forward contribution.
Hi, Hassan.
Okay.
So I have some questions regarding crow, actually.
Okay.
Not necessarily about the mechanism itself, but about going forward.
Mm-hmm.
So my first question would be, so assume that there's a DRAM chip that already implements SMD, the previous work.
Okay.
So, and we want to implement crow on top of this, for example.
Mm-hmm.
So what would it take? Like, what kind of effort or overhead would it need? Like, of course, we would have the area overheads, as you mentioned, but other than that, for example, would we still need to define our new DRAM commands for triggering these operations, or would SMD's interface take care of that?
Yeah. Yeah, good question. So I guess, yeah, using SMD, like these operations can be moved inside DRAM, right? The crow cache can be moved inside DRAM. So that table, the crow table can be implemented inside the DRAM chips too. And yeah, when there's a miss, the chip can decide to open the row with, like at the same time by copying it. But the problem there is that DRAM, the memory controller expects data or expects activations to complete after a specific time interval dictated by the DRAM timing parameters. And so like the TRCD is the time after which the memory controller will issue read command following an activate command. So basically moving these operations inside DRAM will introduce a latency timing parameter difference when doing the copy operation versus when doing the low latency access. So yeah, that problem will need to be solved. I guess that's the biggest problem I see.
So in that case, I think we will need another way of synchronization between the memory controller and DRAM chip about the latency of an activation, let's say, right? So if we leverage all the benefits of crow and activate a row in a really fast way, the memory controller doesn't know about that and it needs to wait. So is that a problem? Did I get it correct?
Yeah, I think so.
Okay.
Yeah, so okay, so like I should also like mention that, so self-managing DRAM. So like by definition, we like designed it only for maintenance operations, right? So reducing activation latency in this example is not necessarily a maintenance operation, but still I am like positive that it might be SMD can still be useful to implement something like crow cache inside the DRAM chip. So like one way to deal with the latency difference that I mentioned is to slightly repurpose the ACNAC signal, right? So it could be used in a way that depending on how many cycles after the activate the memory controller receives that signal, the memory controller may interpret it in different ways. So for example, receiving it after 5 cycles would mean that the activation is rejected, right? So we try it. Receiving it 1 cycle later might mean that, yeah, so your activation is a bit delayed. So you should read 1 cycle or 2 cycle later than you are supposed to. And this is where the row copy operation happens, right? And so similarly, in case of a row head, like there can be basically a way, in the same way, the SMD can inform the memory controller that a low latency operation happens, and you can issue the read command earlier. But what I don't like about this mechanism is that it requires changes on the memory controller side, right? So enabling that, although we sort of hide the operation, we think that we hide the operation under SMD, to perform these low latency accesses, the memory controller still needs to be aware that such a latency reduction mechanism is implemented in those DRAM chips and observe the timings in receiving the ACNAT signals. You see what I mean? So like enabling such a mechanism still has to go into the DRAM standard.
Yes.
Maybe there's a way to implement it without memory control knowing about it, but it doesn't make sense because like fundamentally, like at least the current way the DRAM is accessed in like those packet-based memory systems such as HMC, where like the requests are sent from the memory controller to the like DRAM module like HMC stack in like packetized format, so with serial links. So there, such mechanism can be enabled much more easily. But with these synchronous interfaces, it's more difficult.
Yeah, I understand. Makes sense. Yeah, there are definitely a lot of things to consider about that.
Yeah.
So yeah, thanks for that answer. And I have another question. It's also some hypothetical question. So I'm sure you're aware that there are like these recent works, namely like PyDRAM and Compute DRAM, that show that the current commodity DRAM chips, even though it is not in the specification, somehow support row clone.
Okay.
And yeah, my question would be about like, would you expect some similar chips to already implement Crow as well?
Okay, so let's think about it. So okay, you can perform row copy. Can you also perform simultaneous row activation? Yeah, I'm not sure about that. So yeah, two rows are activated simultaneously in commodity DRAM as like compute DRAM shows, but there's like still some timing difference between the activation of the two rows. So that timing difference might be limitation sort of.
So I think in row clone's case, there's at least 3 nanoseconds or 5 nanoseconds of delay between two activations.
Yeah.
Because you need to change, send a pre-charge in between.
Mm-hmm.
And yeah, I don't know if it's up from Crow's benefits or not, but yeah.
Yeah. Yeah. If it's 3 nanoseconds, it's a lot, right? So like it would, yeah. What's the
so to be fair, I guess it's also that observation is also limited because of the testing infrastructure's limitations, you know. Because yeah, I mean, I think these works didn't try it with like smaller latencies in between two activations because they simply cannot reach to those clock speeds in FPGA platform.
Right, that's true. Yeah. So yeah, so to exploit the full potential, you really need to have a command that will activate the two nodes at the same time.
I remember running some experiments in that line after Quark TRNG. So just to give some background, in Quark TRNG we show that we can well open 4 DRAM rows in quick succession with 2 activate commands, and that means well, what we hypothesize is the second activate command enables 3 rows at the same time. And the first activate opens the other row. So I did some experiments to basically check if the key ID of Crow could apply here. Like if I write the same value to all 4 rows, activate them and read, can I send the read command earlier or not? The difficulty I had was basically there is some sort of guard band in that timing parameter already. So if TRCD is 15 nanoseconds, meaning that you have to wait 15 nanoseconds before sending the first read command after the activate command, that's only in the standard, and you can violate it to some extent, and that will be that to the extent to which you can violate will differ from DIM to DIM and row to row, or basically physical location of where you're accessing, and you can violate it already by quite a lot without observing bit flips. And when you factor that in, it's really hard to see basically what the benefits are when you also factor in what Giray discussed. So there is some limitation from the platform because you can issue those pre-charge activate commands really fast. So that already takes up 4 or 5 nanoseconds. And then you already have these guard bands on TRCD. So it's really hard to measure what you gain out of it. And my experiments, I think, weren't conclusive, but because I didn't do it comprehensively using many different DIMMs. For the DIMM I used, I remember observing some very small improvements on access time.
Yeah. So definitely such kind of experiment needs to be done like in a much more detailed way. So maybe like, as you said, different modules, and also like analyzing the same module over and over again, collecting all the data, because assessing the reliability when the reliability is high to begin with is difficult, right? So you will not observe bit flips often, but maybe you observe a lot of bit flips considering the lifetime of the module.
Yeah. Yeah.
Okay. Yeah.
Hasan, I have a couple of questions on Crow also.
Okay.
So you mentioned this RowHammer mechanism, even though you didn't evaluate it, right? That is essentially remapping based. It's remapping the victim rows to the copy rows, right? So do you think this is a good solution going forward, or it could be part of a good solution?
Yeah. Yeah, it's hard to say so. Like, it's difficult to think of like what would be the overhead of like refreshing these victim rows every time, like the aggressor rows like keeps being activated. You know, like let's say you refresh the victim rows on every 1,000 activation of the aggressor row. So that compared to moving the victim rows once to copy rows. And maybe at very low activation counts, like where like the activation count to cause RowHammer is very low, then maybe such a remapping approach would be useful. But otherwise, when the activation counts, RowHammer activation counts are high, probably refreshing would be easier, to be honest.
Yeah. I mean, I feel the same way, I think, because refreshing is just an activate, whereas remapping is more operations, right?
True.
I mean, even though you have a good support for it, it's still more operations, I think.
Yeah, it's more operations. Yeah, it will only useful like when you have to refresh too often, right? So instead of like refreshing like too often, you can just move it once and.
Exactly, yeah. And also, I think, I agree. If the RowHammer threshold goes down a lot, refreshing itself starts acting as a RowHammer problem. So in those cases, maybe in the extreme cases where the RowHammer threshold is low, this remapping could be part of a solution.
Could be, yeah.
Okay, I have one more question related to Crow. So you covered a lot of, I think, nice use cases that the substrate enables. Are there any other use cases that you thought about but you did not evaluate or discuss?
Okay, another question that requires remembering. Well.
Or maybe coming up with a new use case now.
Yeah, that's what I'm trying to do because I cannot remember.
That's okay if you don't remember. I mean, is it in the paper
Maybe we discussed something in the paper, but I don't remember right now.
Okay, then maybe interested people can look at the paper.
Yeah.
Okay, that's all I have on Crow.
Yeah, before I conclude, I just want to mention some future research directions. We hope and believe that our contributions will enable future research and understanding the characteristics of current and future memory systems and encourage more innovation in the design of such future memory systems. So some promising research directions are more detailed characterization of DRAM behavior. So specifically some like relatively less studied areas are analyzing cell characterization of new devices, especially like as DDR5 is out in the market, and yeah, nobody, at least in the academia, looked at it yet. Nothing is like openly published, so that's definitely promising direction. Impact of aging is also not studied much, and also low temperature operation, which is required in some application areas such as quantum computing and supercomputing. Superconductive computing. Extending Softmc with support for other DRAM standards and even NVM standards could also be interesting. And even extending Softmc for like other users can be useful, or specializing it to be easier to use, even more easy to use and efficient for specific things such as RowHammer. Okay, as another research direction, improving RowHammer attacks and defenses, studying the security properties of RowHammer protection mechanisms of new DRAM chips or DRAM chips that we didn't look at. New DRAM maintenance mechanisms is another research direction. Especially other profiling-based maintenance operations could be useful to look at, or enabling profiling mechanisms directly inside DRAM chips in a way transparent to the memory controller and the rest of the system could be interesting thing to do. Also, SMD self-managing DRAM could potentially be used to aid in DRAM processing. So it could enable interoperability between DRAM processing engine and memory controller. So basically, the DRAM processing engine could request SMD to a local region where it is performing computation to avoid the memory controller accessing the same data at the same time and causing conflicts. And as a last research direction I have in this list is exploiting in-DRAM data movement for other purposes. So more mechanisms that exploit the slow overhead in-DRAM data migration that we enable with Crow. And yeah, so this is the end of my talk, and I'm happy to answer the remaining questions if there are any. And thanks for listening. It has been a very, very long talk. I hope it was interesting to you and I didn't bore you too much.
It was certainly quite interesting. Thanks, Hassan. We should have taken a break somewhere in the middle. Somehow we we missed that.
I never thought of that.
Yeah, Atabak didn't think of it either, apparently, or neither did I.
We were shooting for the record, no? Is it 3 hours and 30 minutes? We will break Minesh's record.
Well, yeah, I don't know. I have maybe Atabak and Guy have, or some other people have questions, but I have some. I'll ask them. I'll ask mine after they ask. Any questions? Or okay, maybe I'll ask. Yeah.
Yeah, there's one that goes all the way back to Softmc. So I guess one aspect we didn't discuss was extensibility into new standards or new memory modules. In particular, I mean, there have been, I don't know if there are still new non-volatile DIMMs that can be plugged into regular DDR slots. So do you think it could be extended to support those devices also?
Yeah. So as far as I know, I think Intel discontinued the project, the Optane memory project. that was like about building NVM that could operate with DDR4-like interface. I'm not sure if it was compatible with the DDR4 directly, but I think it wasn't. It required some like small changes. But yeah, for this kind of NVM that is highly compatible with like DDR5 or like the existing standard that Softmc supports, like enabling support for this is very easy. So so from DDR3 to extend it to DDR4, for example, yeah, it was like relatively easy because like DDR4 adds only a few new DRAM commands and the like high-level operation is very similar. But yeah, perhaps it's a bit more difficult to extend it to other memory types where like changes are much bigger. I'm not aware of any such like widely used memory module that is like significantly different. So for example, I don't think supporting HBM or GDDR or LPDDR is difficult, given that there are FPGA boards with support for this kind of memories, which we can use to prototype Softmc. So for MEM, I guess the interface, depending on the interface, yeah, it might be easy or it might be a bit more difficult.
I see. Yeah, I understand. Okay, thanks.
Maybe I'll ask my questions now. So you've described a good body of work, Hasan, and you're going to defend your thesis in a couple of weeks. I'm curious about your thesis statement. Maybe you have that in the backup slides or.
Oh, I don't think I have it here, but do you want me to?
Yeah, you can share another presentation also if you want. I think it's good to tie all of these things together with what you had, what I had seen, let's say, reading your thesis.
Sure. Okay, I'm almost there.
Sure.
Okay. Yeah, so should I read it out?
Sure.
Understanding DRAM characteristics and operation through rigorous experimentation using real DRAM chips paved the way for developing new mechanisms that significantly improve DRAM performance, energy consumption, reliability, and security.
Okay, that makes sense.
Sort of more visual representation.
Okay. Yeah, I like the representation.
Okay.
And I assume the understanding comes from mainly Softmc based experiments.
Right.
And U-TRR, I think the U-TRR work is an example of that.
Yeah, I think that's the best example among the other works, but yeah, other works like use that understanding in some like other higher level approach.
Okay, makes sense. So all of these 4 works tied together that way. Okay.
Yeah, in some way they do.
Okay. Okay, I have one question looking maybe into the future. Okay, you talked a lot about DRAM. All of these works are about DRAM. Your thesis statement is about DRAM, right? Now let's assume that DRAM ceases to exist and is replaced by some other technology, which is not looking extremely likely today, but who knows about 30 years down the road. Then is your thesis and your observations, your idea still relevant?
Yeah. So I hope at least the high level insights we provide are will be still useful in the future. Specifically for Softmc, we already discussed, right? So like it can be used to like with slight modifications potentially to analyze other types of memories. And yeah, so maybe DRAM is the only memory that is vulnerable to RowHammer. but other types of memory are vulnerable to other disturbance effects. And so like some sort of protection is required. At least the memory we know today, like flash and like other NVM memories, they're all like vulnerable to some sort of like disturbance and like crosstalk effects that would require like a separate attention. And yeah, so like other mechanisms like self-managing DRAM and Crow can also, in my opinion, like at least idea-wise, contribute to these future works that would use different memory types. Like SMD, like specifically, right? So like maintenance operation, I would guess would be required in other memory types. So like flash memories do some sort of maintenance internally. It's not visible. Usually all the operations are visible to the rest of the system, but like the SSDs and like in whatever form factor flash technology is used, there's some like sort of maintenance that is happening. Yeah, yeah, I would say like they already do sort of similar to what we propose in self-managing DRAM, and self-managing DRAM is like very tied to the DRAM technology. Yeah, but I guess yeah, there can be still something there to like take from these works for future memory technologies, depending on what they will be.
And maybe the takeaway would be not starting with a rigid interface, right?
Yeah.
And having some sort of like flexibility that's provided. Yeah, I wasn't suggesting applying this to Flash. I think Flash is a completely different ball game today, right? Because yeah, you have a separate subsystem managing Flash today. But yeah, I think some future memory technology that's relatively closely integrated to the processors, like DRAM, can benefit from the ideas. I agree.
Yeah.
I mean, even for U-TRR, I assume, right? There you have the insight that you can take advantage of the refresh or retention time behavior as side channels to understand whether internally a chip is performing refresh. Potentially that could be used for other types of understanding, right?
Right.
Okay, I think I have one last question. And then I'll leave the floor to others to ask more questions if they wish to. My last question is, this is your PhD thesis work, but I believe you've done a lot of, or contributed to a lot of other work that has gone on during your PhD as well. Can you provide a quick overview of that?
Yeah, so I actually had a slide about that too here in the slide deck, I believe. Okay, this one. So these are not all works, but these are works that are DRAM related. Yeah, I'm not sure. Like, if should I like to talk about a few of them?
No. Yeah, maybe. Yeah, I was going to suggest maybe I'll be putting you on the spot, but if you had to pick, let's say, 3 of them, what do you think are the most interesting or important 3 that you have contributed to?
Yeah, so okay, so I already mentioned trespass. It is this one here. That was published in Security and Privacy in 2020. So therefore, the first time we show that RowHammer protection mechanisms implemented in DRAM chips can be circumvented by some specific RowHammer access patterns. So here in this work, we show that for the first time, we don't understand exactly how DRAM how TRR mechanisms work at that time, but like we had the intuition that and insights that these like protection mechanisms shouldn't be perfect, and then we just like did this work mainly based on some trial and error, and then we also like developed a black box sort of fuzzing approach to generate these patterns automatically by just like trying out like different patterns based on some constraints, such as like utilizing a lot of rows, hammering a lot of rows at the same time, like picking these rows from like different parts of the DRAM, like different banks or the same bank, constraints such that like this. So besides that, maybe like I would like mention a few works that like in a more like summarized way. So like these two works that were published at Sigmatrix both look at DRAM device characteristics. One of them is looking at operation at low voltage and like basically by the different voltages. And the other is looking at the reliability aspect of DRAM when operating it at low latency, right? So like these are the two studies where we rigorously characterize the low voltage and low latency operation of DRAM and show like opportunities there for like reducing the access latency of DRAM or like optimizing maybe some other aspects as well. Recently there was a where that is. Okay, I think I forgot to include that, or maybe this is an old slide. I was going to mention BlockHammer 2, which was published in 2020 as well. In BlockHammer, we like propose that again. We partially discussed this in this talk, but it's the throttling mechanism that we propose to protect against RowHammer. So it's a mechanism that involves like detecting or like finding the malicious application that is responsible for the access pattern that causes this hammering effect, and then isolate it from the others and only throttle accesses from that application. Or like, well, yeah, at a high level, yes. That is the operations for them.
Yeah, it'd be good to add that here. I agree that you're missing it.
Yeah.
It should be HPCA 2021, right?
Yeah, I think I added it, but this is a wrong version.
Yeah, maybe that's an older. Yeah, sure.
Open.
Okay, so those would be the three you would pick.
Yes.
Okay, at least at this point in time.
Well, yeah, I mean, I didn't pick those based on a particular reason, not because I think those are the most important works here. I think all of them are important, but just to pick something. I could have also mentioned Ambit here, like that micro 2017,
sure.
where we show how to do in DRAM like bitwise operations.
Okay, I think what you're saying is there are too many to pick three from.
I guess so. I just
Okay.
I want to make the discussion long.
Okay, yeah, I don't want to make it any longer. Yeah, I don't have any other questions. Thanks for the presentation.
Yeah, thanks a lot for all the comments, feedback, and questions from everybody.
Yeah, Ataberk, Giray, do you guys have any questions, or does anybody else have any questions?
Maybe.
I don't have any questions. Sorry.
Do you plan on working on similar problems after you graduate?
Yeah, maybe. I like memory systems, so yeah, probably I will keep working at least for some time. But yeah, we'll see how things develop over time.
Okay. Yeah, cool. Thanks.
Okay, thanks, Hassan, and thanks everyone for asking questions. If there are no questions, then we're done. Take care.
Okay.